Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast boundary where our solar system meets the infinite darkness between stars. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On October 19th, 2025, a small spacecraft lifts silently from Cape Canaveral into the pre-dawn darkness. IMAP. The Interstellar Mapping and Acceleration Probe weighs no more than a grand piano, yet carries within its modest frame instruments capable of detecting particles that have traveled for decades across the solar system's most distant reaches. The launch vehicle's engines burn with controlled fury, their chemical reactions converting refined petroleum into precise vectors of velocity, imparting just enough momentum to send this quiet explorer toward a point in space where gravitational forces balance in perfect, mathematical stillness. The spacecraft spins slowly as it rises above Earth's protective atmosphere, solar panels unfolding like metallic petals to catch the first glimmers of unfiltered sunlight. Already, cosmic ray detectors begin their patient work, counting high-energy particles that have journeyed from distant supernovas, each one a tiny messenger carrying the signature of stellar death across the galaxy. These particles strike silicon sensors with the faintest of electrical whispers, announcing their presence through delicate clicks that will continue uninterrupted for the duration of IMAP's mission. Each detection represents matter that left dying stars millions of years ago, accelerated by shock waves from stellar explosions, now arriving at this precise moment in Earth's history to reveal secrets about the space between suns. Mission planners have spent more than 2 decades preparing for this launch, knowing that the heliosphere, our solar system's protective magnetic bubble, remains one of the least understood structures in our immediate cosmic neighborhood. The heliosphere extends far beyond Pluto's orbit, reaching into regions where sunlight becomes indistinguishable from starlight, where the familiar warmth of our star gives way to the ancient chill that has pervaded space since the universe first cooled enough for atoms to form. Voyager 1 and Voyager 2 crossed this boundary years ago, but they sampled only 2 points along a surface that spans hundreds of billions of miles, like 2 swimmers touching opposite shores of an ocean whose true extent remains unmapped. IMAP will observe this boundary from a carefully chosen distance, watching how particles from interstellar space interact with the solar wind in a cosmic dance that has continued unchanged since planets first condensed from the disk of gas and dust that surrounded our young sun. The spacecraft's vantage point allows it to see the forest rather than individual trees, to map the global structure of phenomena that previous missions could only sample locally. From its position, IMAP can observe how the entire heliosphere breathes with the sun's 11-year cycle, expanding and contracting like a vast, slow heartbeat that pulses through the darkness between worlds. The mystery deepens with every measurement previous missions have returned. Scientists initially expected the heliosphere's edge to behave predictably, like a simple shockwave where fast-moving solar wind meets the slower, denser interstellar medium. They envisioned a clean boundary, perhaps slightly flattened by the solar system's motion through space, but fundamentally straightforward in its physics. Instead, they discovered a complex dynamic structure that changes shape with solar activity and responds to magnetic fields threaded through the space between stars. The boundary wriggles and shifts, sometimes ballooning outward when the sun grows active, sometimes compressing inward when solar wind pressure drops during quiet periods. Only took 4.5 billion years for us to notice we live inside a bubble that's never held still. The heliosphere's discovery emerged gradually through decades of patient observation. Early space missions detected the solar wind, that steady stream of charged particles flowing outward from the sun's corona at speeds exceeding 1,000,000 miles per hour. Scientists realized this wind must eventually encounter resistance from the interstellar medium, creating a boundary somewhere in the outer reaches of the solar system. But the exact location, shape, and behavior of this boundary remained theoretical until robotic explorers ventured far enough from home to taste the solar system's edge firsthand. As IMAP climbs toward its destination through the vacuum between Earth and its target orbit, the spacecraft carries humanity's most sophisticated attempt to map the invisible architecture of space itself. Its trajectory will carry it to Lagrange point 1, that gravitational sweet spot between Earth and the Sun, where spacecraft can hover indefinitely with minimal fuel consumption, held in place by the delicate balance of competing gravitational fields. This location, discovered by the 18th century mathematician Joseph Louis Lagrange, represents one of 5 points in the Earth-Sun system where the gravitational pulls of both bodies combine to create regions of orbital stability. From this vantage point, positioned 1.5 million kilometers sunward of Earth, IMAP will spend years collecting energetic neutral atoms, ghostly particles that carry information about collisions occurring at the very edge of everything we call familiar. These energetic neutral atoms form when charged particles from the solar wind collide with neutral atoms from interstellar space, stripping away electrons and creating fast-moving neutral particles that travel in straight lines, unaffected by magnetic fields. They arrive at IMAP's detectors like messages in bottles, each one carrying a chemical signature that reveals where it originated and what forces shaped its journey. The spacecraft's instruments can determine not only the direction from which these atoms arrive, but also their energy and composition, gradually building a three-dimensional map of processes occurring billions of miles away. The irony settles gently around the mission's purpose: to understand our cosmic home's boundaries. We must first leave Earth behind and drift in the emptiness between worlds, waiting patiently for messages written in the language of atoms that remember where they have been. IMAP joins a small family of spacecraft that serve as humanity's most distant sentries, mechanical eyes that watch over regions no human will likely visit for centuries, if ever. These robotic explorers extend our senses into the vacuum, translating the subtle interactions of particles and fields into data streams that eventually become human understanding. The spacecraft's instruments operate at temperatures approaching absolute zero, cooled by radiators that face the cosmic background radiation, that faint afterglow of the Big Bang that still whispers through space at just 2.7 degrees above the coldest possible temperature. In this cryogenic environment, sensors achieve the sensitivity necessary to detect individual atoms and measure their properties with extraordinary precision. The contrast seems almost poetic: the coldest human-made instruments ever deployed, designed to study the hottest phenomena in our cosmic neighborhood, where solar wind temperatures exceed 1,000,000 degrees and particle collisions release energies that would vaporize any material substance. Mission scientists anticipate that IMAP's observations will require years to reveal their full significance, as the spacecraft builds up statistical samples of rare events and maps the slow changes that occur as our solar system moves through different regions of the local interstellar medium. The patience required matches the timescales of the phenomena under study processes that unfold over decades and centuries, driven by forces that have shaped the space around stars since galaxies first began to form. only took us until the 21st century to realize that the space between planets is not empty, but filled with invisible rivers of matter and energy that connect our world to the cosmos beyond. 4.5 billion years ago, when Earth was still a molten ball of rock collecting debris from the early solar system, the Sun began to breathe. This stellar exhalation started as nuclear fusion ignited in the star's core, sending streams of charged particles racing outward from the corona at velocities that would carry them past every planet, past every comet, past the orbit of distant Pluto, and into the darkness beyond. The solar wind flows continuously, a river of protons and electrons that has never ceased since our star first achieved stable hydrogen burning in its heart. The wind emerges from the Sun's corona, that ethereal atmosphere visible during total solar eclipses, as delicate streamers of plasma extending millions of kilometers into space. Here, temperatures reach 2 million degrees Celsius, hot enough to strip electrons from atoms and accelerate the resulting charged particles to escape velocity. The corona's magnetic field lines stretch and snap like rubber bands, occasionally launching coronal mass ejections that send billions of tons of solar material racing through the inner solar system. These dramatic events punctuate the steady background flow of particles that constitutes the normal solar wind, creating a complex, ever-changing stream that carries both matter and magnetic fields away from our star. As the solar wind travels outward, it carries with it the Sun's magnetic field, frozen into the moving plasma like iron filings suspended in flowing water. This embedded magnetic field creates the interplanetary magnetic field, a vast spiral structure that extends throughout the solar system. The spiral pattern emerges because the Sun rotates once every 27 days, causing magnetic field lines to curve like water streaming from a rotating sprinkler. By the time solar wind reaches Earth's orbit, these field lines point at an angle of about 45 degrees to the radial direction, creating a magnetic spiral that astronomers call the Parker spiral, named for the physicist who first predicted its existence. The wind speed varies with solar activity and the region of the corona from which it originates. Fast streams emerge from coronal holes regions where magnetic field lines open into space rather than looping back to the solar surface. These high-speed streams travel at 800 kilometers per second, twice the velocity of the slower wind that emerges from the Sun's equatorial regions. When fast and slow streams interact, they create compression regions where particle density increases and magnetic fields strengthen, sending shock waves rippling through the interplanetary medium like waves on a cosmic ocean. Earth sits immersed in this solar wind, protected by its magnetic field from the worst effects of the charged particle bombardment. The planet's magnetosphere deflects most solar wind around our world, but some particles leak through to create the aurora that dance in polar skies. These shimmering curtains of green and red light represent solar wind particles colliding with atmospheric atoms at altitudes of 100 kilometers or more, releasing energy as visible photons that mark the boundary between space and our planet's gaseous envelope. The auroras serve as a constant reminder that Earth exists within the Sun's extended atmosphere, bathed in the stellar wind that connects our world to its parent star. The solar wind's influence extends far beyond the inner planets, carrying its magnetic field and charged particles past Jupiter, Saturn, Uranus, and Neptune. Each giant planet possesses its own magnetic field that interacts with the solar wind, creating magnetospheres that trap charged particles in radiation belts around these distant worlds. Jupiter's magnetosphere stretches so far that it would appear larger than the full moon if visible to human eyes from Earth, encompassing a volume of space larger than the Sun itself. Yet even these immense magnetic structures represent merely local disturbances in the solar wind's steady outward flow toward the edge of the solar system. Pioneer 10 and Pioneer 11, humanity's first emissaries to the outer solar system, detected solar wind particles even beyond Saturn's orbit in the 1970s and early 1980s. These spacecraft confirm that the Sun's influence extends much farther than early theories predicted, reaching into regions where sunlight becomes so faint that solar panels become useless and spacecraft must rely on radioisotope thermoelectric generators for power. The Voyager spacecraft, launched in 1977, continued this exploration, measuring solar wind properties as they traveled toward and eventually beyond the heliopause, the boundary where solar wind pressure finally balances the pressure of the interstellar medium. The wind's density decreases as the square of distance from the Sun, following the same mathematical relationship that governs the intensity of sunlight and gravitational force. At Earth's orbit, each cubic centimeter of space contains about 5 solar wind particles, but by the time the wind reaches the outer planets, this density drops to less than 1 particle per cubic centimeter. Yet the wind's influence remains strong because of its embedded magnetic field, which helps determine how cosmic rays from distant stars penetrate into the inner solar system. Scientists have discovered that the solar wind varies not just with distance from the Sun, but also with the 11-year solar cycle that governs our star's magnetic activity. During solar maximum, when sunspot numbers peak and solar flares become frequent, the solar wind grows stronger and more turbulent. Coronal mass ejections become more common, sending shock waves through the interplanetary medium that can disrupt satellite communications and create spectacular aurora displays on Earth. During solar minimum, the wind becomes more structured and predictable, with clear boundaries between fast and slow streams that create a more orderly pattern of magnetic fields throughout the solar system. The composition of the solar wind reflects the Sun's own chemical makeup, dominated by hydrogen nuclei with smaller amounts of helium, oxygen, carbon, and trace quantities of heavier elements forged in the stellar core or inherited from the primordial cloud that gave birth to the solar system. Isotope ratios in solar wind samples returned by the Genesis mission revealed subtle differences from terrestrial compositions, providing clues about how the solar nebula evolved and how different regions of the early solar system developed their distinct chemical signatures. Only took us 50 years of space exploration to realize the Sun has been telling us its life story through the particles it sends our way. The solar wind's journey from the Sun's corona to the heliopause takes decades, creating a vast conveyor belt of magnetic fields and charged particles that connects different epochs of solar activity. Solar wind particles detected at the edge of the solar system today began their journey when personal computers were just becoming common and the internet was still a research project. This temporal mixing means that the heliosphere contains a historical record of solar activity, with older, slower wind mixing with younger, faster streams in patterns that encode the Sun's magnetic variability over the past several decades. Modern space weather prediction relies heavily on understanding solar wind variations, as these changes drive geomagnetic storms that can damage satellites, disrupt power grids, and affect radio communications on Earth. The Advanced Composition Explorer spacecraft, positioned at the Lagrange point where IMAP now travels, provides continuous monitoring of solar wind conditions, serving as an early warning system for space weather events. This monitoring reveals the solar wind's remarkable consistency despite all its variations. It has blown steadily outward from the Sun for billions of years, creating the heliospheric bubble that shields our solar system from the harsher radiation environment of interstellar space. The wind carries away approximately 1 billion kilograms of solar material every second. Yet this mass loss represents such a tiny fraction of the Sun's total mass that it will continue blowing for billions of years without significantly affecting our star's evolution. This steady exhalation creates the dynamic boundary that IMAP now studies, where our star's influence finally yields to the ancient matter that drifts between stars, carrying with it the chemical signatures of stellar generations that lived and died long before our solar system formed. Only took us until the space age to discover that stars have weather too. The heliosphere emerges where solar wind meets the ancient matter drifting between stars, creating an invisible boundary that has surrounded our planetary neighborhood since the Sun first began its steady nuclear burning. This vast magnetic cocoon extends far beyond the orbit of Pluto, reaching into regions where the Sun appears as merely the brightest star in a field of distant suns. The boundary itself remains largely invisible to human senses, detectable only through the subtle interactions of charged particles and magnetic fields that spacecraft instruments can measure with exquisite precision. Solar wind travels outward from the Sun at speeds exceeding 400 kilometers per second, carrying with it the star's magnetic field lines embedded in the flowing plasma like invisible threads woven through space. For billions of kilometers, this wind encounters virtually no resistance, expanding freely into the near vacuum between planets. The particle density remains so low that a volume of space the size of a basketball would contain fewer atoms than a single breath of Earth's atmosphere. Yet this tenuous medium carries enormous momentum, created by the cumulative effect of countless particles all moving in the same general direction away from our central star. The interstellar medium presents a different kind of emptiness matter, so sparse that early astronomers believed space between stars contained absolutely nothing. Modern measurements reveal that each cubic centimeter of local interstellar space contains roughly one atom, mostly hydrogen with traces of helium and heavier elements forged in ancient stellar cores. This interstellar matter moves through the galaxy at velocities determined by the rotation of the Milky Way itself, creating relative motion between our solar system and the surrounding medium. Our Sun travels through this cosmic fog at approximately 26 kilometers per second, like a ship moving through water, pushing aside the tenuous matter in its path. Where these two populations of matter meet, the physics becomes beautifully complex. The solar wind begins to slow as it encounters increasing resistance from interstellar particles, much as a river slows when it reaches the sea. This deceleration occurs gradually over vast distances, creating a region called the heliosheath, where solar wind particles lose their outward momentum and begin to heat up through compression. The process resembles the formation of a sonic boom, but spread across billions of kilometers and occurring in a medium so thin that traditional concepts of pressure and density require careful redefinition. The termination shock marks the inner boundary of this transition region, located approximately 90 to 100 astronomical units from the Sun, roughly 90 to 100 times the distance between Earth and our star. Here, supersonic solar wind slows to subsonic speeds, converting kinetic energy into heat and magnetic field compression. Voyager 1 crossed this boundary in December 2004, detecting the characteristic signatures of shocked plasma as solar wind began its final transformation before joining the interstellar medium. The shock itself moves inward and outward with changes in solar activity, breathing like a vast, slow lung that responds to the Sun's 11-year magnetic cycle. Beyond the termination shock lies the heliosheath, a turbulent mixing region where solar wind particles gradually lose their solar identity and prepare to join the ancient matter between stars. In this region, magnetic field lines become twisted and tangled as solar and interstellar fields interact, creating complex patterns that deflect cosmic rays and filter the radiation environment throughout the inner solar system. The heliosheath extends from the termination shock outward to the heliopause itself, spanning perhaps 20 to 50 astronomical units depending on the direction from the Sun and the current state of both solar and interstellar conditions. Temperature patterns within the heliosheath reveal the ongoing struggle between solar and interstellar influences. Solar wind enters this region with temperatures exceeding 100,000 Kelvin, but cools through expansion and interaction with cooler interstellar matter. Paradoxically, some measurements suggest that the heliosheath may actually be cooler than theoretical models predicted, indicating that energy dissipation processes operate more efficiently than scientists initially understood. The cooling creates conditions where some solar wind protons can capture electrons from neutral interstellar atoms, forming energetic neutral atoms that travel in straight lines back toward the inner solar system, carrying information about conditions at the boundary. The heliopause itself represents the true edge of solar dominance, where the pressure of solar wind finally equals the pressure of the interstellar medium. This boundary is not a solid surface, but rather a transition zone where the two populations of matter reach equilibrium. Solar wind particles that reach the heliopause have completed a journey lasting decades, having left the Sun's corona when human technology was far less sophisticated than today. Some particles detected at the heliopause today began their outward journey during the early days of space exploration, when the first satellites were just beginning to reveal the existence of the solar wind itself. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. The spacecraft detected an abrupt change in the composition of charged particles around it, as solar wind protons disappeared almost entirely and were replaced by cosmic ray particles accelerated by distant stellar explosions. The magnetic field strength remained surprisingly constant across the boundary, suggesting that solar and interstellar magnetic fields have similar intensities in our local galactic neighborhood. This discovery challenged theoretical models that predicted a more dramatic change in magnetic field properties at the heliopause. The shape of the heliosphere depends on both solar activity and the properties of the local interstellar medium through which our solar system moves. Early models suggested a comet-like structure with a long tail pointing away from the Sun's direction of motion through the galaxy. More recent observations indicate a more complex, asymmetric shape that varies with solar cycle and responds to changes in interstellar conditions. The heliosphere may be more nearly spherical than previously thought, or it may possess multiple tails and complex magnetic field configurations that create regions of enhanced cosmic ray penetration. Ribbon-like structures detected by the Interstellar Boundary Explorer revealed unexpected organization in energetic neutral atoms arriving from the heliopause region. This ribbon appears as a band of enhanced emission roughly 20 degrees wide, curving across the sky in a pattern that seems to trace the local interstellar magnetic field direction. The ribbon's discovery demonstrates that the heliosphere's interaction with interstellar space creates phenomena that simple models cannot predict, suggesting that magnetic field draping and plasma instabilities play important roles in shaping the boundary region. The heliosphere's protective function becomes apparent when considering the cosmic ray environment beyond the heliopause. Galactic cosmic rays, high-energy particles accelerated by supernova shockwaves, and other violent astrophysical processes permeate interstellar space at intensities that would be harmful to life on planetary surfaces. The heliosphere deflects many of these particles, creating a partially shielded environment within the solar system. The protection is not complete, as evidenced by cosmic rays that penetrate to Earth's surface, but it significantly reduces the radiation dose that planetary atmospheres must absorb from galactic sources. Solar cycle variations affect the heliosphere's size and shape over timescales of years to decades. During solar maximum, increased solar wind pressure pushes the heliopause farther from the Sun, expanding the volume of space under direct solar influence. During solar minimum, the boundary contracts inward as solar wind pressure decreases. These changes occur slowly, with pressure waves taking years to propagate from the inner solar system to the heliopause. The result is a dynamic boundary that responds to solar variability with a characteristic lag time that depends on solar wind transit speed and the compressibility of the interstellar medium. Current measurements suggest that our solar system may be entering a different region of the local interstellar medium, with potentially higher density and different magnetic field orientation than the region we have occupied for the past several thousand years. Such changes could alter the heliosphere's size and shape over timescales much longer than human civilization, creating different cosmic ray environments and potentially affecting planetary atmospheres throughout the solar system. Only took us until the 21st century to realize that our cosmic neighborhood has weather patterns too, operating on timescales that span millennia rather than seasons. The gentle irony emerges slowly. This vast magnetic cocoon that protects us from galactic radiation exists only because our Sun continuously loses 1 billion kilograms of its own substance every second, creating the wind that holds interstellar space at bay. The heliosphere represents a delicate balance between stellar output and galactic input, a boundary condition that has persisted for billions of years, yet remains vulnerable to changes in either solar activity or local interstellar conditions. We live inside a bubble blown by our own star, protected from the galaxy's harsh radiation environment by the same solar wind that occasionally disrupts our satellite communications and power grids. At the heliopause, particles that departed the Sun's corona decades ago finally encounter matter that remembers the deaths of stars that lived and died long before Earth existed. This meeting occurs in the profound darkness beyond Pluto's orbit, where sunlight has weakened to the intensity of bright moonlight and temperatures hover just a few degrees above absolute zero. Here, in a transition zone spanning billions of kilometers, solar wind protons that have traveled for 30 to 40 years finally surrender their outward momentum to the gentle but persistent pressure of ancient interstellar atoms. The interstellar medium surrounding our solar system consists primarily of hydrogen atoms that have drifted through space for millions of years, carrying within their electron shells the chemical signatures of stellar nucleosynthesis from generations past. These atoms formed in the nuclear furnaces of massive stars that exhausted their fuel and exploded as supernovas, scattering their processed elements across vast regions of the galaxy. Some interstellar atoms originated in the Big Bang itself, primordial hydrogen that has wandered through cosmic space for 13 billion years, occasionally swept up by passing stars and then released again into the emptiness between suns. The local interstellar cloud through which our solar system currently travels extends roughly 30 light-years in diameter, encompassing several hundred nearby star systems. This cloud formed from the overlapping shock waves of multiple supernova explosions that occurred roughly 10 million years ago, when our ancestors were small mammals learning to navigate an Earth dominated by grasslands and early forests. The explosions carved out a vast cavity in the galactic disk, creating a region of lower density surrounded by walls of compressed gas and dust. Our solar system entered this cavity perhaps 100,000 years ago, during the time when early humans were developing language and beginning to migrate across continents. Temperature measurements within the local interstellar cloud reveal a medium heated to approximately 7,000 Kelvin by the ancient supernova shock waves, yet so tenuous that this heat cannot warm solid objects through conventional thermal contact. The particle density remains roughly 1 atom per cubic centimeter of vacuum far better than anything achievable in terrestrial laboratories. At such densities, atoms travel for years between collisions, moving in nearly straight lines through space until they encounter magnetic fields or other atoms that can alter their trajectories through electromagnetic interactions. The interstellar magnetic field threads through this tenuous medium like an invisible web, with field lines that curve and twist in response to the motions of nearby stars and the rotation of the galaxy itself. This field possesses a strength roughly 100,000 times weaker than Earth's magnetic field at its surface, yet it profoundly influences the behavior of charged particles throughout the local galactic environment. The field lines appear to run roughly perpendicular to the direction of our solar system's motion through space, creating a bow shock structure ahead of the heliosphere, similar to the wake created by a boat moving through water. Neutral interstellar atoms penetrate deep into the solar system, largely unaffected by magnetic fields due to their lack of electric charge. These atoms flow through the heliosphere like a gentle cosmic breeze, with velocities of approximately 26 kilometers per second relative to the Sun. Some reach Earth's orbit and beyond, where they can be detected by sensitive instruments that distinguish their characteristic velocities and compositions from solar wind particles and planetary atmospheric gases. The flow direction points toward the constellation Scorpius, indicating the direction opposite to our solar system's motion through the local interstellar medium. When solar wind protons collide with these neutral interstellar atoms, charge exchange reactions can occur, processes where electrons transfer between atoms, creating new populations of energetic neutral atoms that carry information about conditions at the collision site. These reactions happen most frequently in the outer heliosheath, where solar wind density reaches its maximum value and neutral interstellar atoms begin to accumulate before penetrating deeper into the solar system. The resulting energetic neutral atoms travel in straight lines, unaffected by magnetic fields, carrying their kinetic energy and directional information back toward the inner solar system, where spacecraft like IMAP can detect and analyze them. The collision zone extends across vast distances, creating a gradual transition rather than a sharp boundary between solar and interstellar domains. Solar wind particles slow as they plow through increasing densities of interstellar matter, while interstellar atoms experience heating and ionization as they encounter the hot, magnetized solar wind plasma. The result is a complex mixing region where neither population retains its original properties, and new phenomena emerge from the interaction between two fundamentally different types of cosmic medium. Isotope ratios in interstellar matter reveal the chemical history of our galactic neighborhood, providing evidence for the stellar processes that created the elements heavier than hydrogen and helium. Carbon, nitrogen, and oxygen atoms in the local interstellar medium show abundance patterns that reflect nucleosynthesis in both low-mass and high-mass stars, indicating that multiple generations of stellar evolution contributed to the current composition. Heavy elements like iron and nickel appear in trace quantities, testifying to the supernova explosions that created these elements in the final moments of massive stellar cores. The pressure balance at the heliopause responds to variations in both solar wind strength and interstellar conditions. When solar activity increases during solar maximum, enhanced solar wind pressure pushes the heliopause farther from the Sun, expanding the heliosphere's volume. Conversely, if the solar system encounters a denser region of interstellar space, increased external pressure compresses the heliosphere inward. These changes occur slowly, with adjustment times measured in years or decades as pressure waves propagate across the vast distances involved. Cosmic ray particles accelerated by distant supernova explosions probe the heliopause from the interstellar side, testing the magnetic defenses that partially shield the inner solar system from galactic radiation. These high-energy particles follow complex trajectories determined by magnetic field configurations, with some penetrating deep into the heliosphere while others are deflected back into interstellar space. The cosmic ray intensity measured within the solar system varies inversely with solar activity, demonstrating that solar magnetic fields provide additional shielding beyond the heliopause's basic pressure balance. Voyager 1's passage through the heliopause revealed that the boundary region exhibits a complex, layered structure rather than a simple transition from solar-dominated to interstellar-dominated space. The spacecraft detected multiple crossings and partial crossings, suggesting that the boundary undulates or contains embedded structures that modulate the transition between the two domains. These observations indicate that the heliopause resembles a weather front in planetary atmospheres, with instabilities and turbulent mixing that create variations in local properties along the boundary surface. The mystery deepens when considering that some theoretical models predicted a bow shock ahead of the heliopause, where interstellar matter would be compressed and heated by our solar system's motion through space. Current observations find no clear evidence for such a shock, suggesting either that the interstellar medium flows more smoothly around the heliosphere than expected, or that the shock exists but remains too weak or diffuse for current instruments to detect reliably. The absence of a clear bow shock challenges our understanding of how stellar systems interact with the interstellar medium through which they move. Modern theoretical models attempt to account for the three-dimensional structure of magnetic fields, both within and beyond the heliosphere. Recognizing that the interaction between solar and interstellar magnetic fields creates complex current sheets and field line reconnection events that can dramatically alter local particle populations. These magnetic effects operate on multiple scales, from microscopic plasma physics processes to macroscopic structures spanning significant fractions of the heliosphere's diameter. Only took us decades of direct observation to realize that the solar system's edge resembles an ocean more than a simple boundary. The temporal evolution of this boundary region occurs on timescales much longer than human experience. As our solar system drifts through different regions of the local interstellar medium over periods of tens of thousands of years. Paleoastronomical evidence suggests that changes in interstellar conditions may have influenced Earth's climate history through variations in cosmic ray flux, which affects cloud formation patterns in the atmosphere. The heliosphere thus connects local planetary environments to galactic processes, creating feedbacks that operate across vast ranges of space and time. Radio emissions detected from the heliopause region indicate that plasma waves and instabilities generate electromagnetic radiation at frequencies ranging from a few hertz to several kilohertz. These emissions provide remote sensing capabilities that allow scientists to study boundary conditions without requiring spacecraft to be physically present at the heliopause. The radio signatures appear to vary with solar activity and may offer early warning of changes in boundary structure before those changes can be detected through direct particle measurements. IMAP settles into its gravitational haven at Lagrange point 1, where the competing pulls of Earth and Sun create a pocket of orbital stability that requires almost no fuel to maintain. This mathematical point in space, predicted by Joseph Louis Lagrange in 1772, exists 1.5 million kilometers sunward of Earth, 4 times farther than the Moon, yet close enough that radio signals take only 5 seconds to travel between spacecraft and ground controllers. Here, in this invisible harbor carved by celestial mechanics, IMAP begins its patient vigil over the solar system's most distant boundaries. The spacecraft's arrival at L1 follows a carefully choreographed journey through gravitational fields that have remained mathematically constant since planets first settled into stable orbits around the young Sun. The trajectory designers calculated every small correction burn, every gravitational assist, every subtle course adjustment needed to deliver IMAP to this precise location with minimal fuel expenditure. The mathematics involved date back centuries, yet their application to spacecraft navigation represents one of the most elegant demonstrations of how theoretical physics translates into practical space exploration. From its vantage point, IMAP can observe the entire heliosphere structure without obstruction from planetary magnetic fields or atmospheric interference. Earth's magnetosphere, which extends roughly 10 Earth radii upstream toward the Sun, lies safely behind the spacecraft, ensuring that terrestrial magnetic effects cannot contaminate measurements of particles arriving from the interstellar boundary. The Moon's gravitational influence becomes negligible at this distance, and even Earth's gravity contributes only a gentle, predictable pull that orbital mechanics can accommodate through tiny, occasional thruster corrections. The spacecraft spins slowly at 5 revolutions per minute, a rotation rate chosen to smooth out directional variations in particle flux and ensure uniform exposure of instruments to the cosmic particle environment. This spin creates artificial stability in the zero-gravity environment of interplanetary space, where no air resistance or ground contact exists to provide reference frames. The rotation axis points toward the Sun, allowing solar panels to maintain constant power generation while scientific instruments sweep through complete circles of sky coverage every 12 seconds. Temperature control at L1 requires careful engineering, as the spacecraft receives 30% more solar radiation than objects in Earth's orbit, but cannot rely on atmospheric convection for cooling. Multi-layer insulation blankets and precisely positioned radiators maintain instrument temperatures within narrow operating ranges, some as cold as -100 degrees Celsius for optimal detector sensitivity. The contrast seems almost poetic. Instruments chilled nearly to absolute zero, studying phenomena involving particles heated to millions of degrees in distant shock waves and magnetic reconnection events. IMAP's instruments begin their systematic survey of energetic neutral atoms arriving from the heliopause region, each detection adding one data point to a growing three-dimensional map of processes occurring billions of kilometers away. The spacecraft's interstellar mapping and acceleration probe. CoDICE instrument measures low-energy particles with exquisite precision, distinguishing hydrogen from helium atoms and determining their energies with accuracy sufficient to trace their origins to specific regions of the heliospheric boundary. Higher energy particles trigger the Interstellar Mapping and Acceleration Probe Ultra instrument, which can detect and analyze atoms with energies up to several hundred kiloelectron volts. The detection process itself relies on principles of atomic physics that have remained unchanged since the universe first cooled enough for atoms to form. When energetic neutral atoms strike the spacecraft's detectors, they release their kinetic energy in carefully controlled ways that allow precise measurement of their mass, energy, and direction of arrival. Each detection represents a neutral atom that originated in a collision between solar wind and interstellar matter, carrying information about conditions that existed at the moment of its creation somewhere near the solar system's edge. Cosmic ray measurements provide continuous monitoring of the radiation environment beyond the heliopause, as galactic cosmic rays probe the heliosphere's magnetic defenses and reveal variations in the boundary's effectiveness at excluding high-energy particles from interstellar space. The Interstellar Mapping and Acceleration Probe. Cosmic ray instrument detects particles with energies ranging from tens of mega-electron volts to several giga-electron volts, covering the energy range where solar modulation effects become most apparent and where the heliosphere's influence on galactic cosmic ray flux can be most clearly studied. Data transmission from L1 to Earth occurs through the Deep Space Network, NASA's collection of large radio telescopes positioned around Earth's equator to maintain continuous communication with distant spacecraft. The radio signals carry digital information encoding particle count rates, energy spectra, and directional distributions that ground-based computers will process into scientific understanding. Each day's observations add to a growing database that will eventually reveal how the heliosphere responds to solar cycle variations and long-term changes in interstellar conditions. The spacecraft's autonomy allows it to continue observations even when Earth's rotation temporarily blocks direct radio contact with ground stations. Onboard computers store scientific data and execute pre-programmed observation sequences, adjusting instrument settings automatically in response to changing particle flux levels or solar activity conditions. This independence becomes essential during solar conjunction periods, when the Sun lies directly between Earth and the spacecraft, blocking radio communications for days or weeks at a time. IMAP's orbital mechanics at L1 create a unique perspective on solar wind evolution, as the spacecraft can observe particles that left the Sun's corona just days before their detection, while simultaneously studying neutral atoms that carry information about solar wind conditions that existed decades earlier at the heliopause. This temporal mixing allows scientists to connect current solar activity with boundary conditions that reflect the Sun's behavior from previous decades, creating opportunities to study cause and effect relationships across vast spatial and temporal scales. The Lagrange point stability depends on the gravitational harmony between Earth and Sun. But this stability is not absolute. Small perturbations from lunar gravity, solar radiation pressure, and the gravitational effects of other planets cause IMAP's orbit to drift slowly over time, requiring periodic correction maneuvers to maintain the spacecraft's position within the operationally useful region around L1. These corrections consume tiny amounts of fuel, allowing the mission to continue for many years before propellant reserves become limiting factors. Solar panel efficiency at L1 exceeds terrestrial solar installations by 30% due to the absence of atmospheric absorption and the closer proximity to the Sun. This abundant power supply enables continuous operation of scientific instruments, data processing computers, and communication systems without the power management constraints that limit many deep space missions. The excess power provides margin for unexpected events, instrument heating during cold periods, and extended mission operations beyond the primary mission duration. The view from L1 encompasses the entire Earth-Sun system from a perspective unavailable from any terrestrial vantage point. Earth appears as a pale blue dot against the cosmic background, while the Sun looms as a blazing disk whose surface features become visible through properly filtered instruments. The spacecraft's position allows it to observe coronal mass ejections and solar flares in side view, providing three-dimensional information about how solar disturbances propagate through interplanetary space toward the planets. Particle populations at L1 reflect the complex mixing of solar wind, interstellar matter, and galactic cosmic rays that characterizes the outer heliosphere's environment. IMAP's instruments detect not only the primary populations of interest, but also secondary particles created by nuclear interactions between cosmic rays and spacecraft materials, charged particles trapped in Earth's extended magnetic field, and energetic atoms produced by solar wind interactions with interplanetary dust grains. Sorting these various populations requires sophisticated data analysis techniques that distinguish genuine interstellar signals from local contamination sources. The spacecraft's mission timeline extends over multiple solar cycles, allowing observations of how heliospheric structure evolves with changing solar activity levels. During solar maximum periods, enhanced solar wind pressure pushes the heliopause farther from the Sun, changing the travel time for energetic neutral atoms and altering the geometric relationships between their production sites and detection location. solar minimum conditions create different boundary configurations, potentially allowing cosmic rays to penetrate deeper into the heliosphere and creating different populations of energetic neutral atoms through charge exchange processes. Communication delays between IMAP and Earth create a natural rhythm in mission operations, as commands uploaded to the spacecraft require 5 seconds to reach L1, while telemetry and scientific data require another 5 seconds to return to ground stations. This 10-second round-trip light travel time necessitates careful planning of real-time operations and contributes to the spacecraft's autonomous capabilities. Only took us until the 21st century to position our electronic eyes at the gravitational balance point where we can watch the solar system's boundaries with unblinking patience, measuring particles that remember collisions from the cosmic frontier. The gentle irony settles around IMAP's purpose to study the most distant reaches of solar influence. We anchor our observatory at a point where competing gravitational fields create perfect stillness, a pocket of stability from which to observe the dynamic processes that mark where our star's domain yields to the ancient emptiness between suns. Energetic neutral atoms arrive at IMAP's detectors like messages written in the language of particle physics, each carrying information encoded in its velocity, direction, and energy about collisions that occurred millions of kilometers away at the solar system's edge. These atoms travel in perfectly straight lines through interplanetary space, unaffected by the magnetic fields that deflect charged particles into complex spiral trajectories. Their neutrality makes them ideal messengers from the distant heliosphere boundary, maintaining their directional information throughout journeys that can last months or years from their creation sites to their detection at Lagrange point 1. The creation process begins when fast-moving solar wind protons encounter slow-moving neutral atoms from interstellar space in the outer heliox sheath, where the two populations first begin to mix in significant numbers. During these encounters, electrons can transfer from neutral interstellar atoms to solar wind protons through charge exchange reactions, converting charged solar wind particles into fast-moving neutral atoms while simultaneously ionizing the originally neutral interstellar matter. The newly created energetic neutral atoms inherit the high velocities of their parent solar wind protons but lose their electric charge, allowing them to escape the magnetic fields that would otherwise trap them in the boundary region. These charge exchange reactions occur most frequently where particle densities reach their highest values near the termination shock and in the inner helios sheath, regions where solar wind protons have been compressed and heated by their interaction with the interstellar medium. The reaction probability depends on the relative velocities of the colliding particles and their electronic configurations. With hydrogen atoms showing the highest cross-sections for charge transfer, each reaction represents a microscopic collision between matter that originated in the sun's corona and matter that has drifted through interstellar space for millions of years, creating neutral atoms that carry the kinetic energy of solar wind but travel with the freedom of uncharged particles. IMAP's detection systems can distinguish energetic neutral atoms from the background populations of solar wind, cosmic rays, and local interstellar matter through careful analysis of particle velocities, energies, and arrival directions. The spacecraft's instruments measure each detected atom's mass through time-of-flight techniques, determining whether it consists of hydrogen, helium, or heavier elements. Energy measurements reveal the velocity the atom possessed when it was created, providing information about the solar wind conditions that existed at its collision site when the charge exchange reaction occurred. Directional information proves especially valuable for mapping the three-dimensional structure of the heliosphere boundary, as energetic neutral atoms preserve the direction from which they originated throughout their journey from creation to detection. By measuring arrival directions over periods of months and years, IMAP can construct maps showing how energetic neutral atom production varies across different regions of the heliopause and how these production patterns change with solar cycle variations and seasonal effects related to Earth's orbital motion around the Sun. The energy spectrum of detected atoms reveals the temperature and compression state of solar wind plasma at the boundary regions where charge exchange reactions occur. High-energy atoms indicate hot, fast-moving solar wind that has not yet been significantly decelerated by interaction with the interstellar medium, while lower-energy populations suggest regions where solar wind has been slowed and cooled through expansion or collision with denser interstellar matter. The shape of the energy distribution provides information about the physical processes operating at the boundary, distinguishing between different theoretical models for how solar wind transitions from supersonic to subsonic flow. Temporal variations in energetic neutral atom flux reflect the propagation of solar wind disturbances from the inner solar system to the heliosphere boundary, creating opportunities to study how coronal mass ejections and other solar events affect conditions at distances of 100 astronomical units or more from the Sun. Enhanced production of energetic neutral atoms can indicate the arrival of shock waves or compression regions at the boundary, while decreases in flux may signal the passage of rarefaction regions or changes in interstellar conditions that affect the efficiency of charge exchange processes. The isotopic composition of detected atoms provides clues about nuclear processes operating in the outer heliosphere, where cosmic ray interactions with interstellar matter can create secondary particles through nuclear fragmentation and spallation reactions. Helium-3 atoms produced by these processes carry distinctive signatures that allow scientists to study cosmic ray propagation and energy spectra in regions where direct cosmic ray measurements are difficult or impossible to obtain. Heavy elements in the energetic neutral atom population trace the abundance patterns of interstellar matter and reveal how stellar nucleosynthesis products are distributed throughout the local galactic environment. Angular resolution in IMAP's measurements allows mapping of fine-scale structure within the heliosphere boundary, potentially revealing the influence of the interstellar magnetic field on the heliopause's shape and the locations where cosmic rays most easily penetrate into the solar system. The spacecraft can distinguish between atoms arriving from different directions with angular precision sufficient to identify discrete source regions and track their evolution over the mission duration. This capability becomes especially important for studying the ribbon structure discovered by previous missions, where enhanced energetic neutral atom production occurs in a narrow band across the sky. Background subtraction requires careful analysis to distinguish genuine interstellar signals from contamination by particles produced within the solar system or by interactions between cosmic rays and the spacecraft itself. Solar wind charge exchange with interplanetary neutral atoms creates a foreground population that must be modeled and removed from the data, while cosmic ray interactions with spacecraft materials generate secondary particles that can mimic energetic neutral atom signatures. Ground-based calibration and in-flight monitoring of these background sources ensure that scientific conclusions rest on genuine interstellar observations rather than instrumental artifacts. Data processing algorithms sort detected particles into populations based on their measured properties, assigning each detection to categories such as interstellar pickup ions, solar wind charge exchange products, cosmic ray secondary particles, or genuine boundary-produced energetic neutral atoms. This classification requires sophisticated pattern recognition techniques that account for the statistical nature of particle detection and the overlapping characteristics of different particle populations. Machine learning approaches help identify subtle signatures that distinguish between similar particle types and improve the reliability of population assignments. Statistical analysis of large datasets reveals population characteristics that would remain hidden in individual particle detections, such as the correlation between energetic neutral atom flux and solar wind parameters measured near Earth, or the relationship between cosmic ray intensity and energetic neutral atom production efficiency at the boundary. These correlations provide tests of theoretical models and help scientists understand the complex feedback mechanisms that govern heliosphere evolution over solar cycle timescales. Spatial mapping techniques combine directional measurements from different times during IMAP's mission to build up three-dimensional images of energetic neutral atom source regions, accounting for the spacecraft's orbital motion and the finite travel time of atoms from their creation sites to the detector. The resulting maps reveal the heliosphere's global structure in a way that point measurements from Voyager spacecraft cannot provide, showing how boundary conditions vary with direction from the Sun and how these variations change with time. The mystery deepens as measurements accumulate. Some energetic neutral atoms appear to arrive from directions that theoretical models struggle to explain, suggesting that the heliosphere's interaction with interstellar space creates particle acceleration mechanisms that current theories do not adequately describe. These anomalous populations may indicate the presence of magnetic reconnection sites, shock acceleration processes, or other phenomena that operate at the boundary between solar and interstellar domains. Only took us decades of particle physics to develop instruments sensitive enough to detect individual atoms that remember where they have been. Energy calibration of IMAP's instruments relies on laboratory measurements of detector response to known particle energies, combined with in-flight observations of well-understood particle populations such as solar wind and cosmic rays. This calibration must account for the gradual degradation of detector materials under constant bombardment by energetic particles and the temperature-dependent response characteristics that change as the spacecraft's thermal environment evolves throughout its mission. Regular calibration updates ensure that energy measurements remain accurate over the multi-year duration required to study solar cycle effects. The invisible river of information flows steadily from the heliosphere's edge to IMAP's patient instruments, each detected atom adding one more data point to humanity's growing understanding of how our solar system interacts with the galaxy that contains it. These measurements connect local particle physics processes to global heliospheric structure, revealing how microscopic charge exchange reactions create macroscopic patterns that map the three-dimensional boundary between stellar and interstellar space. The ribbon stretches across the sky like a faint cosmic smile, visible only to instruments sensitive enough to detect the subtle enhancement of energetic neutral atoms arriving from a narrow band that curves through the constellation boundaries of Aquarius, Capricornus, and Sagittarius. This structure, discovered by the Interstellar Boundary Explorer mission in 2009, challenged every theoretical model that scientists had developed to explain the heliosphere's interaction with interstellar space. The ribbon appears roughly 20 degrees wide and extends across more than half the celestial sphere, marking regions where energetic neutral atom production occurs at rates 2 to 3 times higher than surrounding areas. No theoretical framework predicted such organized structure in the supposedly chaotic mixing region where solar wind meets interstellar matter. Early models anticipated a relatively smooth distribution of energetic neutral atoms, perhaps with some enhancement in the direction of the solar system's motion through space, but nothing resembling the well-defined, persistent ribbon that observations revealed. The structure's discovery forced a fundamental reconsideration of how magnetic fields, plasma flows, and particle acceleration processes operate at the heliosphere's boundary, revealing that this distant region possesses organizational principles that remain poorly understood. The ribbon's orientation appears to correlate with the direction of the interstellar magnetic field threading through the local galactic environment, suggesting that magnetic forces play crucial roles in organizing particle populations and energy dissipation processes at the heliopause. Current models propose that the interstellar field lines drape around the heliosphere like magnetic curtains, creating regions where field line geometry becomes particularly favorable for energetic particle production through magnetic reconnection or field line curvature effects. These magnetic configurations may focus particle acceleration processes into narrow zones that produce the observed ribbon structure. Temporal variations in ribbon intensity reveal that this structure responds to solar cycle changes, growing brighter during certain phases of solar activity and dimming during others. The response occurs with a delay of several years, consistent with the time required for solar wind disturbances to propagate from the inner solar system to the heliopause and for the resulting energetic neutral atoms to travel back to observers near Earth. This temporal lag provides a natural laboratory for studying cause and effect relationships between solar variability and boundary phenomena across vast spatial scales. IMAP's improved angular resolution and energy sensitivity will allow more detailed mapping of the ribbon's internal structure, potentially revealing whether it consists of multiple filaments, knots, or other fine-scale organization that previous missions could not resolve. The spacecraft's multi-year observing campaign will track how ribbon properties evolve through different phases of solar activity, providing data needed to test theoretical models that attempt to explain this unexpected structure in terms of magnetic field interactions and plasma physics processes. The ribbon's energy spectrum differs subtly from energetic neutral atoms arriving from other directions, suggesting that the physical processes creating ribbon particles operate under different conditions than those producing the more uniform background flux. Higher energy atoms appear more strongly enhanced in the ribbon direction, indicating that whatever mechanism creates the ribbon preferentially accelerates particles to higher velocities than typical charge exchange processes. This energy dependence provides important clues about the nature of particle acceleration at the heliosphere boundary. Polarization studies of related phenomena in other stellar systems have revealed similar ribbon-like structures around nearby stars, suggesting that the heliosphere's ribbon represents a common feature of stellar wind interactions with interstellar magnetic fields rather than a unique characteristic of our solar system. These observations indicate that magnetic field draping and associated particle acceleration processes may be universal aspects of how stars interact with their local interstellar environments, creating organized structures that persist despite the apparent chaos of plasma turbulence and magnetic reconnection. The ribbon's stability over multiple years of observation suggests that it reflects some fundamental property of the heliosphere interstellar medium interaction rather than a transient phenomenon that might disappear as conditions change. This persistence implies that the underlying physical processes creating the ribbon operate continuously, maintained by steady-state conditions that exist regardless of shorter-term variations in solar activity or interstellar properties. The ribbon may represent a preferred mode of magnetic field organization that naturally emerges when stellar winds encounter magnetized interstellar media. Theoretical models attempting to explain the ribbon invoke complex three-dimensional magnetic field geometries where interstellar field lines become twisted and compressed by their interaction with the expanding heliosphere. In these models, regions of enhanced magnetic field curvature create favorable conditions for particle acceleration through processes analogous to those operating in planetary magnetospheres and stellar coronae. The curved field lines can accelerate charged particles to high energies through magnetic pumping or drift acceleration mechanisms, subsequently converting them to energetic neutral atoms through charge exchange with interstellar neutrals. Alternative theories propose that the ribbon traces regions where the heliopause becomes unstable, developing plasma instabilities that enhance turbulence and particle acceleration locally. These instabilities might arise from differences in magnetic field orientation between solar and interstellar plasmas, creating current sheets that become unstable to tearing modes or other plasma physics processes. The resulting turbulence could accelerate particles more efficiently than simple charge exchange reactions, creating the enhanced fluxes observed in the ribbon direction. Computer simulations of heliosphere interstellar medium interactions have begun to reproduce ribbon-like structures in their output, but only when they include detailed treatments of magnetic field evolution and particle acceleration that were absent from earlier models. These simulations suggest that the ribbon's formation requires a delicate balance between magnetic pressure, plasma pressure, and geometric effects related to field line draping around the heliosphere's curved boundary. Small changes in any of these factors can dramatically alter the predicted ribbon properties, indicating that the structure's existence depends on specific conditions in our local galactic environment. The ribbon's discovery highlights how much remains unknown about plasma physics processes operating under the extreme conditions found at stellar system boundaries. Particle densities in the heliosheath region are millions of times lower than those accessible in laboratory experiments. While magnetic field strengths and geometric scales differ by many orders of magnitude from terrestrial plasma physics facilities, theoretical understanding must rely on extrapolation from laboratory results and numerical simulations that may not capture all relevant physical processes operating in this unique environment. Cosmic ray modulation studies reveal that the ribbon region may also influence how galactic cosmic rays penetrate into the inner solar system, potentially creating directional variations in cosmic ray intensity that correlate with the ribbon's orientation. If confirmed, these correlations would indicate that the same magnetic field structures creating enhanced energetic neutral atom production also affect cosmic ray propagation, linking two apparently separate aspects of heliosphere physics through common underlying magnetic field configurations. The ribbon's width corresponds roughly to the angular size of structures that might be expected if the interstellar magnetic field creates coherent effects over distances comparable to the heliosphere's radius. This scale relationship suggests that the ribbon traces magnetic field lines or current sheets that extend across significant fractions of the heliosphere's boundary, creating organized structure on scales much larger than typical plasma physics phenomena. The organization implies that interstellar magnetic fields can influence heliosphere evolution in ways that simple pressure balance models cannot predict. Seasonal variations in ribbon intensity may result from Earth's orbital motion, creating changing geometric relationships between the spacecraft's viewing angle and the three-dimensional ribbon structure. As Earth moves around the Sun, IMAP's line of sight to different parts of the ribbon changes, potentially revealing structure that extends significantly above and below the ecliptic plane where most previous observations concentrated. These geometric effects must be carefully modeled to distinguish genuine temporal variations from apparent changes caused by viewing geometry. The ribbon's existence raises questions about whether similar structures might exist in other regions of the heliosphere boundary that have not yet been adequately surveyed, or whether the observed ribbon represents only one component of a more complex organizational pattern that becomes visible only when observed with sufficient sensitivity and angular resolution. Future observations may reveal additional ribbons, loops, or other structures that collectively map the full three-dimensional architecture of magnetic field interactions at the solar system's edge. Only took us until the 21st century to discover that our solar system's boundary is decorated with organized structure that defies simple theoretical understanding, revealing that the interface between stellar and interstellar space creates phenomena that require new physics to explain. The ribbon hangs in space like a cosmic question mark, challenging our assumptions about how magnetic fields and plasma flows create order from apparent chaos at the edge of everything we call home. Ancient cosmic rays seek entry into the solar system like persistent travelers testing every path through the heliosphere's magnetic defenses, carrying energies accumulated during million-year journeys across the galaxy. These high-energy particles originated in violent astrophysical events that occurred long before human civilization emerged on Earth, supernova explosions that scattered processed stellar material across vast regions of space, accelerating protons, helium nuclei, and heavier elements to velocities approaching the speed of light. Each cosmic ray particle represents matter forged in stellar cores and explosively dispersed through shockwaves that can accelerate particles for thousands of years after the initial explosion. The galactic cosmic ray environment surrounding our solar system maintains an intensity level that has remained relatively constant for millions of years, regulated by the rate of supernova explosions throughout the Milky Way and the efficiency with which their shockwaves can accelerate particles to high energies. Roughly one cosmic ray particle strikes each square centimeter of space every second, creating a steady background radiation that permeates the entire galaxy. These particles carry energies ranging from hundreds of millions of electron volts to beyond 10 to the 20th power electron volts, energies so extreme that the highest energy cosmic rays possess more kinetic energy than baseballs thrown by major league pitchers, concentrated into individual atomic nuclei. The composition of galactic cosmic rays reflects the nuclear processes that created them, with roughly 87% consisting of hydrogen nuclei, 12% helium nuclei, and the remaining 1% heavier elements up to iron and beyond. This abundance pattern differs significantly from normal stellar atmospheres, showing enhanced concentrations of elements like lithium, beryllium, and boron that form through nuclear fragmentation when primary cosmic rays collide with interstellar gas during their galactic travels. These secondary elements serve as chronometers, allowing scientists to estimate how long cosmic ray particles have wandered through the galaxy before reaching our solar system. The heliosphere acts as a partial shield against galactic cosmic rays, deflecting many lower energy particles while allowing higher energy cosmic rays to penetrate relatively freely into the inner solar system. This modulation occurs because cosmic ray particles, being charged, interact strongly with the solar wind's embedded magnetic field lines and the turbulent magnetic structures that permeate the heliospheric medium. Lower energy cosmic rays, with gyroradii comparable to heliospheric magnetic field structure scales, experience strong scattering and can be excluded entirely from inner heliospheric regions during periods of high solar activity. Solar cycle variations dramatically affect cosmic ray intensity throughout the solar system, with cosmic ray flux at Earth's orbit varying by factors of 2 or more between solar minimum and solar maximum conditions. During solar maximum, enhanced solar wind, magnetic field strength, and increased turbulence create more effective barriers against cosmic ray penetration, reducing the flux of galactic particles reaching planetary orbits. Solar minimum conditions allow deeper cosmic ray penetration, as weaker and more organized magnetic fields provide less scattering and deflection of incoming galactic particles. The energy dependence of solar modulation creates characteristic spectral signatures in cosmic ray energy distributions measured within the heliosphere, with lower energy particles showing stronger modulation effects than higher energy cosmic rays that possess sufficient rigidity to penetrate magnetic barriers more easily. This energy dependence allows scientists to study the detailed structure of heliospheric magnetic fields by analyzing how different cosmic ray energies respond to solar cycle changes and heliospheric boundary conditions. Cosmic ray gradients measured by spacecraft at different heliocentric distances reveal the three-dimensional structure of solar modulation, showing how cosmic ray intensity increases with distance from the Sun as the influence of solar magnetic fields weakens. Pioneer and Voyager spacecraft measurements demonstrated that cosmic ray intensity continues to increase beyond the orbit of Saturn, reaching maximum values only after crossing the heliopause into true interstellar space where solar magnetic fields can no longer affect galactic particle propagation. The termination shock creates complex effects on cosmic ray propagation, potentially accelerating some particles to higher energies while simultaneously creating barriers that exclude others from the inner helios sheath region. Shock acceleration mechanisms can energize particles through multiple encounters with converging plasma flows, gradually increasing their energies through statistical acceleration processes that operate over timescales much longer than individual particle shock interactions. These locally accelerated particles create distinct populations that can be distinguished from galactic cosmic rays through their composition and energy spectra. Magnetic field irregularities in the helios sheath region scatter cosmic rays through pitch angle diffusion and energy diffusion processes that depend on the detailed structure of magnetic turbulence at scales ranging from particle gyroradii to macroscopic features of the heliospheric boundary. The efficiency of these scattering processes determines how effectively cosmic rays can propagate from interstellar space into the inner solar system, creating the observed modulation patterns that vary with both solar activity and the properties of local interstellar magnetic fields. IMAP's cosmic ray measurements will provide the most detailed observations yet obtained of how galactic cosmic rays interact with the evolving heliospheric boundary. Tracking changes in cosmic ray intensity, energy spectra, and arrival directions as solar activity varies and as our solar system moves through different regions of the local interstellar medium. The spacecraft's position at Lagrange point 1 allows continuous monitoring of cosmic ray conditions without interference from planetary magnetic fields, providing a baseline for understanding cosmic ray modulation throughout the solar system. Anisotropy measurements reveal that cosmic rays do not arrive uniformly from all directions, but show small directional preferences that reflect the influence of local galactic magnetic fields and the solar system's motion through the cosmic ray background. These anisotropies vary with cosmic ray energy and with solar cycle phase, providing information about how magnetic field structures on scales ranging from the heliosphere to the local galactic environment affect particle propagation over vast distances and timescales. The relationship between cosmic ray intensity and climate on Earth remains an active area of research, with some evidence suggesting that cosmic ray variations might influence cloud formation processes in the atmosphere through ionization of air molecules that serve as condensation nuclei. If confirmed, such connections would link heliospheric physics to terrestrial climate variability, creating feedback mechanisms that connect local planetary environments to galactic processes operating over much larger scales of space and time. Heavy cosmic ray nuclei provide unique information about stellar nucleosynthesis processes and supernova explosion mechanisms, as their abundances reflect the nuclear processes that created them in massive stellar cores before their explosive dispersal through shockwave acceleration. Elements heavier than iron in the cosmic ray population trace the most extreme nucleosynthesis environments and the most energetic explosion processes, offering insights into stellar evolution scenarios that cannot be studied through any other observational techniques. Isotope measurements in cosmic ray samples reveal details about the timescales involved in cosmic ray acceleration and propagation, as radioactive isotopes decay during their galactic journeys and provide natural clocks for estimating travel times between acceleration sites and detection locations. Short-lived isotopes indicate recently accelerated cosmic rays, while the absence of very short-lived species sets upper limits on acceleration timescales and propagation speeds through the galactic magnetic field environment. The solar system's motion through different regions of the local interstellar medium may create long-term variations in cosmic ray intensity as our heliosphere encounters regions with different magnetic field orientations, densities, and cosmic ray populations. Paleoclimatic evidence suggests that such variations may have influenced Earth's atmospheric chemistry and climate evolution over geological timescales, creating connections between stellar astronomy and terrestrial environmental history that operate over millions of years. Ultra-high-energy cosmic rays, with energies exceeding 10 to the 18th power electron volts, represent the most extreme particles in the known universe and may originate from active galactic nuclei. Gamma-ray bursts, or other exotic astrophysical sources located far beyond our local galactic neighborhood. These particles penetrate heliospheric magnetic barriers easily due to their extreme energies. But their rarity makes statistical studies difficult, and their sources remain among the greatest mysteries in high-energy astrophysics. Only took us until the space age to discover that we live immersed in a steady rain of particles that remember the deaths of stars, carrying across the galaxy the processed remains of stellar cores that lived and died before our solar system formed, now seeking passage through our star's magnetic domain on journeys that began when Earth was still a molten ball of rock collecting debris from the early solar nebula. Our solar system drifts through a warm, thin region of space known as the local interstellar cloud, a cavity carved by ancient stellar explosions that occurred roughly 10 million years ago when our planet's continents were still shifting toward their modern configurations. This cloud stretches approximately 30 light-years across, encompassing several hundred nearby star systems in a bubble of heated gas and dust that bears the chemical signatures of multiple supernovae. The cloud's boundaries remain poorly defined, merging gradually with denser regions of the interstellar medium that record different episodes of stellar death and stellar birth across our local galactic neighborhood. Temperature measurements within the local cloud reveal matter heated to approximately 7,000 Kelvin by the shock waves from ancient supernovae, yet so tenuous that this thermal energy cannot warm solid objects through conventional heat transfer. The particle density averages roughly 1 atom per cubic centimeter, a vacuum far better than anything achievable in terrestrial laboratories, yet dense enough to exert measurable pressure on the heliosphere's outer boundary. At such extreme rarefaction, individual atoms travel for years between collisions, moving in nearly straight lines through space until electromagnetic forces alter their trajectories. The chemical composition of the local cloud reflects the nuclear alchemy that occurred within massive stars before their explosive deaths scattered processed elements throughout this region of the galaxy. Hydrogen dominates, representing roughly 70% of all atoms, while helium accounts for most of the remainder. Heavier elements, oxygen, carbon, nitrogen, iron, and dozens of others appear in trace quantities that encode the details of stellar nucleosynthesis and supernova explosion dynamics. These abundance patterns differ subtly from those measured in other regions of the galaxy, indicating that local stellar evolution has followed a somewhat different path than the galactic average. Our solar system entered the local cloud approximately 100,000 years ago, during the time when early humans were developing language and beginning to migrate across continents. Before entering this region, our solar system traveled for millions of years through even more tenuous regions of space, encountering different interstellar conditions that may have significantly altered the heliosphere's size and structure. Astronomical evidence suggests that changes in interstellar density and magnetic field orientation can compress or expand the heliosphere by factors of 2 or more, potentially affecting cosmic ray flux throughout the inner solar system. The boundaries of the local cloud reflect the complex history of stellar evolution in our galactic neighborhood, where multiple generations of massive stars have lived brief, violent lives before exploding as supernovae that reshape the interstellar medium across vast volumes of space. These explosions create expanding shock waves that sweep up surrounding matter, compressing it into dense shells while leaving behind hot, rarefied cavities that can persist for millions of years. Our local cloud represents one such cavity, still cooling and expanding from the supernova explosions that created it roughly 10 million years ago. Magnetic fields thread through the local cloud with strengths of approximately 3 microgauss, roughly 100,000 times weaker than Earth's magnetic field at its surface, yet strong enough to influence the behavior of charged particles throughout this region of space. The field orientation appears to be roughly perpendicular to our solar system's direction of motion, creating a bow shock-like structure where our heliosphere plows through the magnetized interstellar medium. This magnetic geometry affects how cosmic rays propagate through the local galactic environment and influences the detailed structure of the heliospheric boundary. Neutral interstellar atoms from the local cloud penetrate deep into the solar system, flowing past planetary orbits with velocities of approximately 26 kilometers per second relative to the Sun. These atoms represent pristine samples of interstellar matter, largely unaffected by solar processes until they undergo charge exchange reactions with solar wind particles in the outer heliosphere. Their isotopic compositions provide direct measurements of interstellar abundances, revealing how supernova explosions and stellar winds have processed matter in our local galactic region over the past several million years. The local cloud's motion through the galaxy carries it past other stellar systems and interstellar structures on timescales of millions of years, creating a slowly changing environment for all the stars contained within its boundaries. Our Sun travels through this medium at approximately 26 kilometers per second, fast enough to create a detectable ram pressure that affects the heliosphere's structure, but slow enough that major changes in interstellar conditions occur over timescales much longer than recorded human history. The cloud's internal turbulence creates smaller-scale variations that might affect heliospheric structure over timescales of thousands or tens of thousands of years. Dust grains within the local cloud carry information about solid materials processed by stellar winds and supernova explosions, providing samples of condensed matter that formed under the extreme conditions found in stellar atmospheres and explosion shock waves. These microscopic particles, typically smaller than the wavelength of visible light, absorb and scatter starlight in ways that reveal their compositions and size distributions. Some dust grains reach the inner solar system, where spacecraft and ground-based collectors can capture them for detailed laboratory analysis. The transition zones surrounding the local cloud mark regions where matter processed by different stellar populations begins to mix, creating gradients in chemical composition, temperature, and magnetic field properties that extend across multiple light years. Our solar system's trajectory will carry it through these transition regions over the next several thousand years, potentially exposing the heliosphere to different interstellar conditions that could significantly alter cosmic ray modulation and the detailed structure of the heliospheric boundary. Velocity measurements of nearby stars reveal that the local cloud participates in the general rotation of the galactic disk, while also exhibiting internal motions that reflect its origin in supernova-driven turbulence. These velocity patterns help astronomers reconstruct the explosion history that created the cloud and predict how it will evolve over the next several million years as it continues to expand and cool. The cloud's future evolution will determine the interstellar environment that our solar system will encounter as it continues its galactic orbit. Temperature gradients within the local cloud create pressure variations that drive slow bulk motions of interstellar matter over timescales much longer than human experience. These motions redistribute matter and energy throughout the cloud, gradually erasing the signatures of the original supernova explosions while creating new structures through gravitational and magnetic instabilities. The resulting evolution connects local interstellar physics to larger-scale processes that govern star formation and galactic chemical evolution. Radio observations of the local cloud reveal ionized components that complement direct measurements of neutral atoms, providing information about regions too hot or too highly ionized to be detected through optical absorption lines or neutral atom flux measurements. These ionized regions may trace shock fronts or magnetic reconnection sites where different populations of interstellar matter interact, creating phenomena analogous to those observed at the heliospheric boundary, but operating on much larger spatial scales. The local cloud's interaction with nearby stellar systems creates a network of overlapping heliospheres and interstellar bow shocks that modify the local galactic environment in ways that affect cosmic ray propagation and interstellar chemistry. Some nearby stars possess much stronger stellar winds than our Sun, creating larger heliospheres that may influence cosmic ray populations throughout our local galactic neighborhood. Other stars have already evolved beyond their main sequence phases, creating different types of stellar winds that inject different chemical compositions into the interstellar medium. Theoretical models of local cloud evolution predict that our solar system will exit this region within the next 10,000 to 50,000 years, entering either denser regions of the galactic disk or other supernova-processed cavities with different physical properties. Such transitions could dramatically alter heliospheric structure, potentially compressing the heliopause inward by factors of several and significantly increasing cosmic ray flux throughout the inner solar system. These changes would occur slowly enough to be imperceptible during individual human lifetimes, but rapidly enough to create detectable effects in paleoclimatic records. The mystery deepens when considering how the local cloud interfaces with larger-scale galactic structures, such as the local bubble, a much larger cavity that encompasses our local stellar neighborhood and extends several hundred light-years in diameter. The relationship between these nested structures reveals the hierarchical nature of interstellar organization, where stellar explosions create cavities within cavities, each with its own characteristic temperature, density, and chemical composition that reflects different episodes of stellar evolution and galactic dynamics. Only took us until the 20th century to discover that the space between stars is not empty but filled with the processed remains of stellar generations that lived and died before our solar system formed, creating the warm, thin medium through which we now drift on our journey around the galaxy. Carrying Earth and its cargo of life through an ocean of stellar ash that remembers explosions from the deep cosmic past, magnetic field lines weave through the darkness between stars like invisible threads in a cosmic tapestry, connecting the local interstellar cloud to vast networks of galactic magnetic structure that extend across thousands of light-years. These field lines, typically 3 microgauss in strength, millions of times weaker than a refrigerator magnet, yet strong enough to guide the motion of charged particles across interstellar distances, thread through the tenuous matter surrounding our solar system with geometric precision that reflects billions of years of galactic evolution. The interstellar magnetic field represents one of the galaxy's fundamental organizational principles, channeling matter and energy flows in ways that influence star formation, cosmic ray propagation, and the large-scale architecture of galactic structure. The field's orientation in our local galactic neighborhood appears to run roughly perpendicular to the solar system's direction of motion through space, creating a configuration that significantly affects how our heliosphere interacts with the surrounding interstellar medium. This geometry arises from the complex interplay between galactic rotation, stellar winds from nearby stars, and the shock waves from ancient supernovae that shape the local interstellar cloud. As our solar system plows through this magnetized medium at 26 kilometers per second, the interstellar magnetic field lines drape around the heliosphere's boundary like streamlines flowing around an obstacle in a magnetized fluid. The magnetic field structure exhibits organization on multiple scales, from microscopic flux tubes that guide individual particle motions to macroscopic features that extend across entire spiral arms of the galaxy. Within the local cloud, turbulent motions create tangled magnetic field configurations that vary on scales ranging from astronomical units to light years, producing the complex field line geometries that influence cosmic ray scattering and heliospheric boundary dynamics. This turbulence arises from the stirring action of stellar winds and the passage of shock waves from distant stellar explosions, creating a constantly evolving magnetic landscape that changes too slowly for human instruments to detect directly. Polarization measurements of starlight reveal the magnetic field's direction through its effect on dust grain alignment, as elongated interstellar dust particles tend to orient themselves perpendicular to magnetic field lines through electromagnetic torques. These observations show that the local interstellar magnetic field maintains a relatively coherent direction over distances of several light years, suggesting that large-scale galactic magnetic structures dominate over local turbulent motions in determining field orientation. The coherence extends far enough to influence the magnetic environment encountered by multiple nearby stellar systems, creating common magnetic conditions across significant volumes of our local galactic neighborhood. Faraday rotation measurements using pulsars as radio sources provide additional information about interstellar magnetic field strength and direction. As radio waves from these rapidly rotating neutron stars undergo polarization changes that depend on the magnetic field strength along their propagation paths. These measurements reveal that magnetic field strengths vary by factors of several across our local galactic region, with stronger fields concentrated in certain directions that may reflect the influence of nearby stellar associations or the passage of old supernova shock waves that compressed and amplified pre-existing galactic magnetic fields. The interstellar field's interaction with the heliosphere creates complex current sheet structures, where magnetic field lines of different orientations come into contact and can undergo reconnection events that accelerate particles and generate electromagnetic emissions. These current sheets may contribute to the ribbon structure detected in energetic neutral atom measurements. As regions of enhanced magnetic field curvature and current density provide favorable sites for particle acceleration processes that operate more efficiently than simple charge exchange reactions between solar wind and neutral interstellar atoms. Magnetic pressure within the interstellar medium contributes significantly to the total pressure that balances solar wind pressure at the heliopause, particularly in regions where field lines become compressed or tangled by their interaction with the expanding heliosphere. The magnetic contribution can exceed thermal pressure by factors of several in some directions, creating asymmetries in heliospheric structure that depend on the detailed geometry of interstellar magnetic field draping around the solar wind bubble. These pressure variations help explain why the heliosphere's shape deviates from simple spherical symmetry and why the heliopause distance varies significantly with direction from the Sun. Theoretical models of magnetic field draping around the heliosphere predict the formation of magnetic flux ropes and other coherent structures that could persist for extended periods and influence particle acceleration and transport processes throughout the outer heliosphere. These structures arise when field lines with different orientations interact and become twisted around each other, creating rope-like configurations that can trap and accelerate charged particles through magnetic pumping and curvature drift mechanisms. The predicted structures remain largely theoretical, as direct magnetic field measurements at the heliopause are limited to the 2 points where Voyager spacecraft cross the boundary. The galactic magnetic field participates in the overall rotation of the Milky Way, but with velocity patterns that differ from those of stars and gas clouds due to the field's tendency to resist bending and twisting through magnetic tension forces. This differential rotation creates shearing motions that can amplify magnetic field strength through dynamo processes while simultaneously creating instabilities that generate turbulence and magnetic reconnection events. The resulting field evolution operates on timescales of millions to billions of years, connecting local interstellar magnetic conditions to the long-term evolution of galactic magnetic structure. Cosmic ray propagation through the local cloud depends critically on magnetic field structure. As charged particles follow field lines and scatter off magnetic irregularities during their journeys from acceleration sites to the solar system, the field's turbulent structure creates a complex maze that cosmic rays must navigate, with scattering rates that depend on particle energy, field strength, and the power spectrum of magnetic fluctuations across different spatial scales. Understanding this propagation requires detailed knowledge of magnetic field structure that extends far beyond direct observational capabilities. Magnetic reconnection events in the interstellar medium can accelerate particles to high energies through processes similar to those observed in planetary magnetospheres and stellar coronae, potentially contributing to the galactic cosmic ray population or creating distinct populations of locally accelerated particles. These events occur when magnetic field lines with opposite orientations come into contact and rapidly reconfigure their connectivity, releasing stored magnetic energy as kinetic energy of accelerated particles. The frequency and efficiency of interstellar reconnection events remain poorly constrained by current observations. The magnetic field's influence extends beyond particle dynamics to affect the thermal evolution of interstellar matter through magnetohydrodynamic wave propagation and dissipation processes that can heat or cool the medium depending on local conditions. Magnetic waves generated by stellar winds and supernova explosions propagate through the interstellar medium for thousands of years, carrying energy that eventually dissipates as heat through various plasma physics mechanisms. This magnetic heating may contribute significantly to maintaining the local cloud's elevated temperature long after the original supernova explosions that created it. IMAP's magnetic field measurements will provide new constraints on interstellar magnetic field structure through observations of how magnetic field draping affects energetic particle populations and heliospheric boundary dynamics. The spacecraft's long-duration observations will reveal how magnetic field variations correlate with changes in cosmic ray intensity and energetic neutral atom production, providing tests of theoretical models that attempt to connect local magnetic field structure to larger-scale galactic magnetic phenomena. Numerical simulations of magnetohydrodynamic turbulence in the interstellar medium reveal that magnetic field structure exhibits fractal properties, with similar statistical characteristics appearing across a wide range of spatial scales from astronomical units to hundreds of light years. This scale invariance suggests that universal physical processes govern magnetic field evolution in low-density, weakly collisional plasmas, creating organizational principles that apply throughout the galaxy's interstellar medium. The fractal structure implies that magnetic field measurements at any location provide information about field properties across much larger volumes of space. The interstellar magnetic field connects our local galactic environment to the Milky Way's global magnetic structure, which exhibits spiral patterns that trace the galaxy's rotation while also showing evidence for large-scale magnetic loops and chimneys that extend far above and below the galactic disk. These connections mean that changes in galactic magnetic field structure, driven by processes such as galactic collisions or episodes of enhanced star formation, can eventually influence magnetic conditions throughout the local cloud and affect heliospheric physics over timescales of millions of years. Only took us until the late 20th century to develop instruments sensitive enough to detect magnetic fields so weak that they barely influence matter denser than individual atoms, yet strong enough to organize the architecture of space itself across distances that dwarf the solar system, creating invisible highways that guide cosmic rays and channel stellar winds through the vast emptiness that separates one star from another in the galactic disk where we make our home. The heliosphere breathes with the sun's 11-year heartbeat, expanding and contracting like a vast organism responding to the rhythmic changes in solar magnetic activity that have pulsed through the solar system for billions of years. During solar maximum, when sunspot numbers peak and coronal mass ejections become frequent, enhanced solar wind pressure pushes the termination shock and heliopause farther from the sun, inflating the heliospheric bubble by distances that can exceed 10 astronomical units. During solar minimum, the quieter sun produces weaker solar wind that allows interstellar pressure to compress the heliosphere inward, reducing its volume by significant fractions as the boundary retreats toward the inner solar system. These cyclical changes unfold slowly across the vast distances involved, with pressure waves taking years to propagate from the sun's corona to the heliopause at speeds determined by the local sound velocity in the solar wind plasma. A coronal mass ejection that erupts from the sun today will not reach the termination shock for 18 months or more, and its influence on heliopause position may not become apparent for several additional years as the boundary gradually adjusts to the altered pressure balance between solar wind and interstellar medium. This temporal lag creates a complex relationship between solar activity and heliospheric structure, where boundary conditions reflect a mixture of current and historical solar behavior. Solar cycle variations affect not only the heliosphere's size, but also its shape. As the solar wind's magnetic field structure becomes more complex and turbulent during periods of high solar activity, the sun's magnetic field reverses polarity every 11 years, creating transition periods where magnetic field lines become highly twisted and the solar wind carries enhanced levels of magnetic turbulence into the outer heliosphere. These periods of magnetic complexity can create asymmetric pressure distributions that deform the heliosphere from its more symmetric solar minimum configuration into shapes that depend on the detailed evolution of solar magnetic field patterns. Temperature variations within the heliosheath respond to solar cycle changes as compressed solar wind alternately heats and cools with the varying strength of solar wind dynamic pressure. During solar maximum, shocked solar wind in the heliosheath can reach temperatures exceeding 1 million Kelvin as strong solar wind encounters enhanced resistance from interstellar pressure. Solar minimum conditions allow the shocked plasma to cool through expansion and reduced compression, creating temperature variations that affect charge exchange reaction rates and the production of energetic neutral atoms that carry information about boundary conditions back to observers in the inner solar system. The cosmic ray modulation that results from solar cycle variations creates one of the most dramatic demonstrations of how solar activity influences conditions throughout the heliosphere, with cosmic ray intensity at Earth varying by factors of 2 or more between solar minimum and solar maximum. During solar maximum, the enhanced and more turbulent solar wind magnetic field provides more effective scattering of galactic cosmic rays, reducing their flux throughout the inner solar system. Solar minimum conditions allow cosmic rays to penetrate more easily, as the weaker and more organized magnetic field presents fewer obstacles to particle propagation from interstellar space. Energetic neutral atom production rates vary significantly with solar cycle phase, as the efficiency of charge exchange reactions depends on the density, temperature, and flow velocity of solar wind plasma in the outer heliosheath, where most reactions occur. Enhanced solar wind during solar maximum increases the collision rate between solar wind protons and neutral interstellar atoms, creating more energetic neutral atoms that can be detected by spacecraft instruments. However, the higher temperatures and more turbulent conditions during solar maximum also affect the energy spectra of produced atoms, creating time-variable signatures that encode information about solar cycle evolution. The ribbon structure detected in energetic neutral atom measurements shows clear evidence of temporal evolution correlated with solar cycle changes, growing brighter and more distinct during certain phases of solar activity while fading during others. These variations occur with the characteristic delay expected for signals that originate at the heliopause and must travel for months or years to reach detection instruments near Earth. The ribbon's response to solar cycle changes provides a natural laboratory for studying cause and effect relationships across the vast scales of the outer heliosphere. Long-term observations spanning multiple solar cycles reveal that the heliosphere's response to solar activity exhibits memory effects, where boundary conditions depend not only on current solar wind properties, but also on the history of solar activity over previous years or decades. This memory arises because the outer heliosphere contains solar wind that departed the Sun many years ago, creating a temporal mixing of plasma from different epochs of solar activity. The result is a boundary region that reflects the integrated history of solar variability rather than just instantaneous solar conditions. Magnetic field configurations at the heliopause undergo systematic changes related to solar cycle evolution. As the polarity and complexity of solar magnetic field carried by the solar wind create time-varying current sheet structures and magnetic reconnection opportunities. During solar cycle transitions, when the Sun's magnetic field reverses polarity, the heliosheath contains solar wind with opposite magnetic polarities that can interact through reconnection processes, potentially creating enhanced particle acceleration and affecting the efficiency of cosmic ray exclusion from the inner heliosphere. Seasonal variations superimpose additional complexity on solar cycle effects, as Earth's orbital motion around the Sun creates changing geometric relationships between observing spacecraft and the three-dimensional structure of heliospheric boundaries. These geometric effects can masquerade as genuine temporal variations in boundary properties, requiring careful analysis to distinguish between real solar cycle effects and apparent changes caused by viewing geometry. The seasonal effects become particularly important for understanding directional variations in energetic neutral atom flux and cosmic ray intensity. IMAP's multi-year observing campaign will capture heliospheric evolution through different phases of solar cycle 25, providing the first comprehensive dataset showing how energetic neutral atom production and cosmic ray modulation respond to solar activity variations with the improved sensitivity and angular resolution available from modern instrumentation. The spacecraft's observations will span from solar minimum through solar maximum and potentially into the following solar minimum, creating opportunities to study both short-term and long-term heliospheric evolution. The amplitude of solar cycle variations in heliospheric properties depends on local interstellar conditions, with the heliosphere showing stronger responses to solar activity when immersed in lower density regions of the interstellar medium, and more muted responses when surrounded by higher density material that provides stronger external pressure. Our current location within the local interstellar cloud creates moderate interstellar pressure that allows clear solar cycle signatures while preventing extreme variations that might occur in very low-density regions of space. Coronal hole evolution drives much of the solar cycle variation in solar wind properties, as these regions of open magnetic field lines produce the fast, steady solar wind streams that dominate heliospheric dynamics. The size, location, and persistence of coronal holes change systematically through the solar cycle, creating predictable patterns in solar wind speed and magnetic field strength that propagate through the heliosphere and eventually influence boundary conditions at the heliopause. Understanding coronal hole evolution thus becomes crucial for predicting heliospheric response to solar activity. Solar energetic particle events create additional temporal variations in outer heliosphere conditions, as shockwaves from major solar flares and coronal mass ejections accelerate particles to high energies that can reach the heliopause region within months, rather than the years required for normal solar wind propagation. These energetic particles can temporarily modify plasma conditions in the heliosheath and potentially affect charge exchange reaction rates and magnetic field configurations near the boundary, creating impulsive signatures that complement the more gradual solar cycle effects. The relationship between solar cycle variations and interstellar boundary conditions provides insights into fundamental plasma physics processes operating under extreme conditions that cannot be reproduced in terrestrial laboratories. The heliosphere serves as a natural laboratory where solar cycle changes create controlled experiments in plasma physics, magnetic field interactions, and particle acceleration processes across spatial scales, ranging from microscopic gyroradii to macroscopic boundary structures spanning billions of kilometers. Theoretical models attempting to predict heliospheric evolution must account for the complex interplay between solar cycle variations, interstellar conditions, and the three-dimensional magnetic field structures that govern particle transport and boundary dynamics. These models require sophisticated numerical simulations that can follow plasma evolution across the vast range of temporal and spatial scales involved, from the rapid changes associated with individual solar events to the gradual evolution of boundary structure over multiple solar cycles. Only took us several decades of space-based observations to recognize that our solar system pulses with the rhythm of its central star, creating a dynamic boundary that breathes in response to solar activity while maintaining the fundamental architecture that has protected planetary environments from galactic radiation for billions of years, demonstrating that even the most distant reaches of solar influence remain intimately connected to processes occurring in the Sun's corona 93 million miles away. The solar wind begins its journey from the Sun's corona at temperatures exceeding 2 million degrees Celsius, yet gradually cools to a mere few thousand degrees by the time it reaches the heliopause, surrendering its thermal energy across the vast expanse that separates our star from the interstellar medium. This cooling process unfolds over distances spanning more than 100 astronomical units, creating temperature gradients so gentle that the change occurs imperceptibly across scales larger than planetary orbits. The wind's temperature evolution reflects fundamental thermodynamic processes operating in an expanding plasma that transitions from the extreme conditions near the Sun to the frigid environment of deep space. Adiabatic expansion drives most of the cooling, as solar wind plasma spreads into the ever-increasing volume of interplanetary space while doing work against the gravitational field of the Sun and the magnetic forces that constrain its motion. The expansion follows laws of thermodynamics that apply equally to stellar atmospheres and terrestrial gases. Yet the extreme conditions in the heliosphere create plasma behaviors that push these familiar laws to their limits. At the coronal base, where solar wind originates, plasma densities exceed 10 billion particles per cubic centimeter. But by the time the wind reaches Earth's orbit, this density has dropped to fewer than 10 particles per cubic centimeter. The cooling rate varies with solar activity and the specific coronal regions from which different solar wind streams originate. Fast streams from coronal holes maintain higher temperatures than slow streams from the solar equatorial regions, creating a complex thermal structure that persists throughout the heliosphere. These temperature differences affect how efficiently different solar wind populations interact with interstellar matter at the boundary, influencing charge exchange reaction rates and the production of energetic neutral atoms that carry thermal information back toward the inner solar system. Shockwave heating provides temporary departures from the general cooling trend, as compression regions where fast and slow solar wind streams interact create localized heating that can raise plasma temperatures by factors of several above their pre-shock values. These interaction regions propagate outward through the heliosphere like moving furnaces, carrying enhanced thermal energy to the termination shock and beyond. The heating occurs through processes analogous to those operating in stellar atmospheres and supernova remnants, where converging plasma flows convert kinetic energy into random thermal motion of particles. Temperature measurements throughout the heliosphere reveal that the solar wind never quite achieves thermal equilibrium with the surrounding interstellar medium, maintaining temperatures significantly higher than the 7,000 Kelvin characteristic of the local interstellar cloud, even after decades of expansion and cooling. This temperature difference drives heat conduction processes that operate slowly due to the low particle densities involved, creating thermal gradients that extend across the entire outer heliosphere and contribute to the pressure balance that determines heliopause location. The termination shock creates the most dramatic temperature change in the solar wind's journey, compressing and heating the plasma as it transitions from supersonic to subsonic flow. Post-shock temperatures in the heliosheath can exceed several 100,000 Kelvin, representing a temporary reversal of the general cooling trend as kinetic energy of directed flow converts to random thermal motion through the shock heating process. This heating occurs through collective plasma processes that operate more efficiently than simple particle collisions, demonstrating the exotic physics that governs plasma behavior under the extreme conditions found at the solar system's edge. Beyond the termination shock, thermal evolution in the heliosheath becomes more complex, as the shocked solar wind plasma gradually cools through expansion while simultaneously undergoing heating through magnetic reconnection events and turbulent dissipation processes. The competition between cooling and heating creates temperature structures that vary significantly with direction and distance from the termination shock, producing thermal gradients that influence particle transport and magnetic field evolution throughout the outer heliosphere. IMAP's observations of energetic neutral atoms will provide indirect temperature measurements throughout the heliosheath. As the energy spectra of detected atoms reflect the thermal properties of the solar wind plasma, where charge exchange reactions occur, higher temperature regions produce more energetic neutral atoms, while cooler regions generate atoms with lower average energies, creating temperature maps that reveal thermal structure across vast regions of the outer heliosphere that remain inaccessible to direct measurement. Electron and proton temperatures can differ significantly in the low-density plasma environment of the outer heliosphere, where collisional processes occur too infrequently to maintain thermal equilibrium between different particle species. Electrons, with their much smaller masses, respond more quickly to heating and cooling processes, while protons retain thermal energy longer and can maintain higher temperatures in regions where electrons have already cooled. These temperature differences affect plasma physics processes such as wave propagation and instability development. Heat conduction through the heliosphere operates according to classical transport theory. Yet the extreme length scales involved mean that thermal equilibration times exceed the age of the solar system by many orders of magnitude. Local thermal imbalances can persist for millions of years without significant change, creating temperature structures that reflect historical conditions rather than current energy balance. This thermal memory effect means that temperature measurements throughout the heliosphere provide information about solar activity and boundary conditions that existed long before direct observations became possible. The interstellar medium surrounding our solar system maintains its temperature of approximately 7,000 Kelvin through a delicate balance between heating from dilute starlight and cosmic rays and cooling through radiation from trace amounts of heavier elements that can emit photons efficiently at these temperatures. This temperature represents a compromise between various heating and cooling mechanisms operating in the low-density environment between stars, where traditional concepts of thermal equilibrium require careful redefinition. Temperature gradients at the heliopause create thermoelectric effects that can drive electric currents and contribute to magnetic field generation in the boundary region, adding complexity to the electromagnetic processes that govern particle acceleration and transport. These thermoelectric phenomena operate through the same physical principles that govern terrestrial thermoelectric devices, yet under conditions so extreme that quantum mechanical effects may become important for determining transport coefficients and electromagnetic response functions. Plasma instabilities driven by temperature gradients can develop throughout the heliosphere, particularly in regions where different populations of solar wind with significantly different temperatures come into contact. These instabilities can generate electromagnetic waves that propagate throughout the heliospheric medium, carrying energy and momentum in ways that affect global heliospheric structure. The instabilities operate on timescales ranging from minutes to years, depending on the spatial scales and temperature differences involved. Solar cycle variations create systematic changes in solar wind temperature throughout the heliosphere, as enhanced heating during solar maximum periods produces hotter plasma that takes longer to cool during its journey to the boundary. These temperature variations propagate outward through the heliosphere like thermal waves, creating time-variable heating rates at the heliopause that affect charge exchange processes and energetic neutral atom production. The thermal waves move much more slowly than the plasma itself. As heat conduction velocities remain much lower than bulk flow speeds, radiative cooling becomes increasingly important in the outer heliosphere, where plasma densities drop low enough that radiation can escape without significant reabsorption, and where temperatures remain high enough that atomic and ionic transitions can produce observable emission lines. This cooling mechanism operates more efficiently for plasma containing trace amounts of heavier elements, creating composition-dependent cooling rates that can influence the thermal evolution of different solar wind populations. The temperature of space itself. The cosmic microwave background radiation at 2.7 Kelvin provides the ultimate thermal sink toward which all matter in the universe gradually equilibrates over cosmological timescales. While this temperature remains far below anything achieved in the heliosphere, it represents the fundamental temperature floor that governs radiative cooling processes and defines the thermal environment into which our solar system expands as it moves through the galaxy. Laboratory plasma experiments cannot reproduce the combination of low density, large-scale length, and intermediate temperature that characterizes heliospheric thermal processes, making the heliosphere itself the only available laboratory for studying thermal evolution under these extreme conditions. Theoretical understanding must rely on extrapolation from laboratory results and computer simulations that may not capture all the relevant physics operating in this unique environment. Only took us until the space age to develop instruments sensitive enough to measure temperatures in regions so remote and tenuous that individual atoms travel for years between collisions. Yet where thermal processes operating over decades and centuries determine the structure and evolution of the vast bubble that surrounds our planetary system and shapes the radiation environment throughout the realm we call home. Data streams from IMAP flow steadily toward Earth through radio waves that carry digital information encoding the three-dimensional architecture of our solar system's most distant boundaries, gradually revealing structure that has remained hidden since planets first formed around the young sun. Each transmitted data packet contains measurements of individual particle detections, magnetic field vectors, and instrument status information that ground-based computers will process into maps showing how solar wind pressure, interstellar matter density, and magnetic field configurations vary across the vast spherical surface where our star's influence finally yields to the ancient emptiness between suns. The mapping process requires years of patient observation, as IMAP's instruments must accumulate statistically significant samples of rare events while the spacecraft's orbital motion and Earth's revolution around the Sun provide changing perspectives on the distant heliospheric boundary. Energetic neutral atoms detected by the spacecraft arrive from directions distributed across the entire celestial sphere, but with flux levels that vary by orders of magnitude depending on the efficiency of particle production processes operating in different regions of the heliopause. Building maps with sufficient angular resolution to reveal fine-scale structure requires collecting millions of individual particle detections over observation periods spanning multiple solar cycles. Angular resolution in the resulting maps depends on the geometric relationship between the spacecraft's position, the size of its detector apertures, and the statistical precision achievable with finite counting rates from distant particle sources. IMAP's instruments can distinguish arrival directions to within a few degrees, sufficient to separate contributions from different regions of the heliospheric boundary, and to track how source regions evolve over timescales of months and years. This angular precision represents a significant improvement over previous missions, enabling detailed studies of ribbon structure and other fine-scale phenomena that were barely detectable in earlier surveys. Three-dimensional reconstruction techniques combine measurements of particle arrival directions, energies, and detection times to infer the spatial distribution of source regions throughout the outer heliosphere, accounting for the finite travel times required for energetic neutral atoms to propagate from their creation sites to the detection instruments. The reconstruction process must consider that atoms detected simultaneously may have originated from charge exchange reactions that occurred at different times, creating temporal mixing effects that complicate the relationship between observed flux variations and actual changes in boundary conditions. Statistical analysis methods sort the accumulated particle detections into populations based on their measured properties, distinguishing between energetic neutral atoms produced by charge exchange at the heliopause, pickup ions created when interstellar atoms become ionized within the heliosphere, cosmic ray secondary particles generated by nuclear reactions, and instrument background events that can mimic genuine astrophysical signals. This classification requires sophisticated pattern recognition algorithms that account for overlapping characteristics between different particle populations and the statistical uncertainties inherent in individual measurements. Systematic uncertainties in the mapping process arise from imperfect knowledge of instrument response functions, calibration drifts that occur during extended space exposure, and contamination by particles produced within the solar system rather than at the interstellar boundary. Controlling these uncertainties requires extensive ground-based calibration before launch, regular in-flight monitoring using well-understood particle populations, and cross-calibration with measurements from other spacecraft when overlapping observations become available. Temporal evolution tracking reveals how heliospheric structure responds to solar cycle variations, interstellar weather changes, and the solar system's motion through different regions of the local galactic environment. The maps show not only the current distribution of particle sources, but also how this distribution has changed over the years of IMAP's mission, providing insights into the dynamic processes that govern boundary evolution on timescales comparable to human technological development. Correlation analysis between IMAP's observations and solar wind measurements near Earth reveals cause and effect relationships that operate across the vast scales of the heliosphere, connecting solar activity variations to boundary phenomena through propagation delays that reflect the time required for disturbances to travel from the Sun's corona to the heliopause. These correlations provide tests of theoretical models and help scientists understand how local solar system phenomena connect to global heliospheric structure. Magnetic field mapping emerges from analysis of particle arrival directions and energy spectra, as charged particles follow magnetic field lines and experience acceleration or deceleration depending on local field configurations. While IMAP cannot measure magnetic fields directly at the heliopause, The spacecraft's observations of particle populations provide indirect information about field strength, direction, and topology in regions where direct measurements remain impossible with current technology. Comparison with Voyager spacecraft. Data provides ground truth for IMAP's mapping techniques, as the two interstellar probes have measured plasma and magnetic field conditions directly at specific points along the heliospheric boundary. The agreement between IMAP's remote sensing results and Voyager's in situ measurements validates the mapping methodology while revealing the advantages and limitations of each observational approach for studying heliospheric structure. Computer simulations of heliospheric physics provide theoretical frameworks for interpreting IMAP's observations, but the spacecraft's measurements often reveal phenomena that existing models cannot explain adequately. These discrepancies drive improvements in theoretical understanding and motivate the development of more sophisticated numerical simulations that can account for previously neglected physical processes operating at the solar system's edge. Data fusion techniques combine IMAP's observations with measurements from other space missions, ground-based observations, and theoretical calculations to create comprehensive models of heliospheric structure that incorporate all available information sources. This interdisciplinary approach reveals connections between local particle measurements and global heliospheric phenomena that would remain hidden if different data sources were analyzed in isolation. Machine learning algorithms help identify patterns in IMAP's large datasets that might escape human recognition, particularly for phenomena that develop slowly over the multi-year duration of the mission, or that involve subtle correlations between different measured quantities. These artificial intelligence techniques complement traditional statistical methods by discovering relationships that were not anticipated by theoretical models or previous observational experience. Error propagation analysis tracks how uncertainties in individual measurements affect the reliability of scientific conclusions drawn from the accumulated dataset, providing confidence estimates for different aspects of the derived heliospheric maps. This analysis becomes particularly important when combining measurements from different time periods, different instrument modes, or different spacecraft to create unified pictures of boundary structure and evolution. Real-time monitoring capabilities allow mission scientists to respond to unexpected phenomena as they develop, adjusting observation strategies to focus on particularly interesting events or regions that show unusual activity. This adaptive approach maximizes the scientific return from IMAP's finite mission duration by concentrating observational resources on the most scientifically valuable measurements. Legacy data products from IMAP's mission will provide reference datasets for future heliospheric research, establishing baseline measurements of boundary structure during specific solar cycle conditions and interstellar environment states. These reference measurements will become increasingly valuable as our solar system continues its motion through the local galactic environment, encountering different interstellar conditions that may significantly alter heliospheric structure over timescales of thousands to millions of years. Visualization techniques translate IMAP's numerical datasets into intuitive graphical representations that reveal spatial patterns and temporal evolution in ways that facilitate scientific understanding and public communication. These visualizations range from simple two-dimensional sky maps showing particle flux distributions to sophisticated three-dimensional renderings that illustrate the complex geometric relationships between different regions of the heliospheric boundary. Archive and distribution systems ensure that IMAP's observations remain accessible to the international scientific community long after the mission ends, providing data resources that will support heliospheric research for decades to come. The archived data will enable future scientists to reanalyze IMAP's measurements using improved techniques and theoretical frameworks that have not yet been developed, extending the mission's scientific impact far beyond its operational lifetime. Quality assessment procedures validate the scientific integrity of IMAP's measurements through independent analysis by multiple research groups, peer review of analysis methods, and comparison with theoretical predictions and other observational datasets. These quality controls ensure that scientific conclusions based on IMAP's observations meet the rigorous standards required for advancing human understanding of fundamental astrophysical processes. Only took us until the 21st century to develop the computational tools and statistical methods needed to transform streams of individual particle detections into comprehensive maps of invisible architecture spanning billions of kilometers, revealing the three-dimensional structure of boundaries so distant and tenuous that they exist more as transitions between different states of nearly empty space than as surfaces in any conventional sense. Beyond the heliopause lies the local galactic environment, a vast ocean of matter and energy shaped by the collective influence of hundreds of nearby stars and the lingering effects of stellar explosions that occurred millions of years ago when continents on Earth were drifting toward their current positions. This region extends for dozens of light years in all directions, encompassing the local interstellar cloud and the broader local bubble within which our solar system makes its orbital journey around the galactic center. Here, the processed remains of stellar nucleosynthesis mix with primordial matter that has wandered through space since the early universe, creating a medium whose composition tells the story of stellar evolution across our local galactic neighborhood. The density of matter in this region averages roughly 1 atom per cubic centimeter, yet varies by factors of 10 or more depending on local conditions shaped by stellar winds, supernova shock waves, and the gravitational influence of nearby star-forming regions. Dense molecular clouds lurk at the edges of the local bubble, containing thousands of atoms per cubic centimeter and serving as stellar nurseries where new generations of stars condense from gravitationally collapsing gas and dust. Between these clouds lie vast regions of even lower density, evacuated by ancient supernova explosions and containing fewer atoms than the best vacuum chambers achievable in terrestrial laboratories. Temperature patterns throughout the local galactic environment reflect the complex history of energy injection from stellar sources, with regions heated by supernova shock waves maintaining temperatures of millions of degrees, while other areas cool to the few thousand degrees typical of neutral interstellar matter. The hottest regions emit X-rays that can be detected by space-based observatories, revealing the three-dimensional structure of supernova-heated gas that extends hundreds of light years from the explosion sites. These X-ray observations show that our solar system lies within a network of hot, low-density cavities created by multiple supernova explosions over the past 10 million years. Magnetic fields pervade the local galactic environment with typical strengths of a few microgauss, organized into structures that trace the influence of stellar winds, supernova explosions, and the galactic rotation that slowly stirs matter throughout the disk. These fields guide the motion of charged particles across interstellar distances, creating invisible highways that connect stellar systems and channel cosmic ray propagation throughout our local galactic region. The field configurations change slowly over time scales of millions of years as new stars form and old ones explode, gradually reshaping the magnetic architecture that governs particle transport and energy dissipation. Chemical compositions in the local galactic environment reveal the nuclear processes that created the elements heavier than hydrogen and helium, with abundance patterns that reflect contributions from both low-mass stars that exploded as Type Io supernovae and high-mass stars that ended their lives as core collapse supernovae. Isotope ratios provide clues about the timing of these stellar explosions and the efficiency of different nucleosynthesis processes, while the spatial distribution of various elements traces how stellar ejecta have mixed throughout the local interstellar medium over millions of years. Dust grains scattered throughout the region absorb and scatter starlight, creating the interstellar reddening that affects observations of distant stars and reveals information about grain compositions and size distributions. These microscopic particles, typically smaller than the wavelength of visible light, formed in the atmospheres of evolved stars and the expanding shells of supernova explosions, carrying within their crystalline structures direct samples of matter processed by stellar nuclear burning. Some dust grains eventually reach the inner solar system, where they can be captured by spacecraft and analyzed in terrestrial laboratories. Cosmic ray populations in the local galactic environment maintain intensities that have remained relatively constant for millions of years, regulated by the balance between particle injection from supernova explosions and energy losses through propagation effects and escape from the galactic disk. The cosmic ray spectrum extends from energies of millions of electron volts to beyond the highest energies achievable in particle accelerators, with the highest energy particles likely originating from active galactic nuclei or other exotic sources located far beyond our local stellar neighborhood. Neutral interstellar atoms flow through the local galactic environment at velocities determined by the complex interplay between stellar gravity, radiation pressure, and magnetic forces, creating streams and eddies that can persist for thousands of years before turbulent mixing erases their identities. Some of these atoms penetrate deep into stellar systems, providing direct samples of interstellar matter that can be analyzed by sensitive instruments aboard spacecraft like IMAP, revealing the chemical and isotopic compositions of matter that has never been processed by stellar nucleosynthesis. The local bubble, the largest structure in our immediate galactic neighborhood, extends several hundred light-years in diameter and contains dozens of stellar systems within its low-density interior. This cavity was carved by a series of supernova explosions that occurred within a moving group of massive stars, each explosion adding energy to expand and maintain the bubble against the inward pressure of surrounding denser material. The bubble's walls, compressed by the outward moving shock waves, show enhanced densities and altered magnetic field configurations that affect cosmic ray propagation and star formation processes throughout our local galactic region. Stellar winds from nearby stars contribute continuously to the local galactic environment, with massive stars producing particularly powerful winds that can excavate their own cavities within the surrounding interstellar medium. These winds carry processed stellar material into interstellar space, enriching the medium with elements created by nuclear burning in stellar cores and contributing to the slow chemical evolution that gradually increases the metallicity of interstellar matter over galactic timescales. Turbulence pervades the local galactic environment at all observable scales, driven by the stirring action of stellar winds, supernova explosions, and gravitational instabilities that develop in regions where matter density exceeds critical thresholds. This turbulence creates a complex hierarchy of eddies and vortices that mix matter and energy across vast ranges of spatial scales, from microscopic plasma physics processes to macroscopic structures spanning multiple light years. The motion of our solar system through this environment creates a bow shock structure where our heliosphere plows through the magnetized interstellar medium. Though current observations have not yet detected clear evidence for this predicted shock, the absence of a detectable bow shock suggests either that the interstellar medium flows more smoothly around stellar systems than theoretical models predict, or that the shock exists but remains too weak or diffuse for current instruments to observe reliably. Gravitational effects from nearby stellar systems create subtle perturbations in the orbits of comets in the outer regions of our solar system, occasionally sending these icy bodies into the inner solar system where they become visible as they sublimate in the solar radiation. These gravitational influences operate over timescales of millions of years and distances measured in light years, demonstrating that stellar systems remain gravitationally connected even across the vast emptiness that separates one star from another. Star formation activity in nearby molecular clouds will eventually reshape the local galactic environment as new massive stars form, evolve, and explode over the next several million years. These future supernovae will inject fresh energy into the local bubble and may alter the magnetic field configurations and density distributions that currently characterize our local interstellar neighborhood, potentially affecting the heliospheric boundary conditions that shield our solar system from galactic radiation. IMAP's observations provide a unique window into this local galactic environment through measurements of particles that have been processed by the interaction between our heliosphere and the surrounding interstellar medium. The spacecraft's data reveal not only conditions at the heliospheric boundary, but also properties of the interstellar matter and magnetic fields that extend far beyond the solar system's direct sphere of influence. Connecting local solar system phenomena to the broader galactic context within which our planetary system has evolved. The relationship between local and global galactic structure becomes apparent through observations of how magnetic field directions, density patterns, and chemical compositions in our immediate neighborhood reflect larger-scale processes operating throughout the Milky Way's spiral arms. Our location within the galactic disk provides a representative sample of conditions that exist throughout much of the galaxy, making studies of our local environment relevant for understanding how stellar systems interact with interstellar matter throughout the universe. Only took us until the era of space-based astronomy to recognize that the space immediately surrounding our solar system contains a rich ecosystem of matter and energy flows that connect us to stellar processes operating across our local galactic neighborhood, revealing that we exist not in isolation, but as part of a vast, slowly evolving network of stellar systems embedded within the processed remains of countless generations of stars that lived and died to create the chemical elements from which planets and life itself eventually formed. Years of patient observation gradually illuminate how our solar system interacts with the galaxy that contains it, revealing processes that have operated unchanged for billions of years while our planetary system completed hundreds of orbits around the galactic center. IMAP's accumulated measurements build a comprehensive picture of boundary phenomena that connect the familiar realm of planets and asteroids to the vast, ancient currents of matter and energy that flow between stars. The spacecraft's data streams reveal that our heliosphere exists not as an isolated bubble, but as part of a dynamic network of stellar wind interactions that extends throughout our local galactic neighborhood. Each stellar system creating its own heliospheric cavity while participating in larger-scale processes that govern the evolution of interstellar matter. The emerging understanding shows that heliospheric boundaries serve as laboratories where fundamental plasma physics processes operate under conditions impossible to reproduce in terrestrial experiments, creating phenomena that bridge microscopic particle interactions and macroscopic structures spanning billions of kilometers. Magnetic reconnection events at the heliopause accelerate particles to energies comparable to those found in planetary radiation belts, yet operate in a medium so tenuous that individual particles travel for months between collisions. Shockwave formation occurs through collective plasma instabilities rather than simple gas compression, demonstrating exotic physics that applies throughout the universe wherever stellar winds encounter interstellar matter. The temporal evolution, revealed by IMAP's multi-year dataset, demonstrates that heliospheric structure responds sensitively to both solar activity variations and changes in the local interstellar environment through which our solar system moves. Solar cycle effects propagate through the heliosphere like slow waves, taking years to reach the boundary and additional years to modify the particle populations that carry information back toward the inner solar system. These propagation delays create complex feedback loops where current boundary conditions reflect the integrated history of solar activity over previous decades, connecting present-day observations to solar behavior that occurred when space exploration was in its infancy. Interstellar weather patterns emerge from the data as our solar system encounters different regions of the local interstellar cloud, revealing that the space between stars possesses its own meteorology, operating on scales of light years and time scales of millennia. Density variations, magnetic field changes, and temperature fluctuations in the interstellar medium create corresponding variations in heliospheric structure, demonstrating that planetary environments remain connected to galactic processes through the mediating influence of stellar wind interactions at distances far beyond any planetary orbit. The three-dimensional architecture mapped by IMAP reveals asymmetries and complex structures that challenge simple theoretical models of how stellar winds interact with interstellar matter. The ribbon structure, discovered in energetic neutral atom observations, traces magnetic field configurations that extend across significant fractions of the heliospheric boundary, suggesting that interstellar magnetic fields play crucial roles in organizing particle acceleration and transport processes. These magnetic effects operate through mechanisms analogous to those found in planetary magnetospheres and stellar coronae, yet scaled up to dimensions that dwarf anything found within the solar system proper. Chemical fingerprints in the detected particle populations reveal the nuclear processes that created the elements flowing through our local galactic environment, tracing matter back to its origins in stellar cores and supernova explosions that occurred millions of years before Earth formed. Isotope ratios encode information about the efficiency of different nucleosynthesis pathways and the timescales over which stellar ejecta mixed throughout the interstellar medium, providing direct measurements of galactic chemical evolution processes that operate too slowly for direct observation, but whose cumulative effects determine the composition of matter from which new stellar systems form. Energy balance calculations based on IMAP's observations reveal that the heliosphere efficiently converts the directed kinetic energy of solar wind into random thermal motion and magnetic field energy, with most of the dissipation occurring in the outer Helios heath, where solar wind finally surrenders its outward momentum to interstellar pressure. This energy conversion occurs through a cascade of plasma physics processes that operate across vast ranges of spatial and temporal scales, from microscopic particle gyration to macroscopic magnetic field reconfigurations that span the entire outer heliosphere. Cosmic ray modulation studies using IMAP's data demonstrate that the heliosphere provides partial but significant shielding against galactic radiation, reducing cosmic ray intensity throughout the inner solar system by factors that vary with solar cycle phase and boundary configuration. The shielding efficiency depends on complex interactions between solar magnetic fields, interstellar magnetic fields, and the turbulent structures that develop where these two populations meet and mix. Understanding these interactions becomes crucial for assessing radiation environments for future interstellar missions, and for interpreting paleoclimatic evidence that may reflect cosmic ray variations over geological timescales. The global circulation patterns revealed by particle transport modeling show that matter and energy flow through the heliosphere in organized patterns that persist despite the apparently chaotic nature of plasma turbulence and magnetic reconnection at the boundary. These circulation patterns create preferred pathways for cosmic ray penetration and establish the geometric framework within which phenomena like the ribbon structure develop and evolve. The patterns reflect the fundamental symmetries and asymmetries in the configuration of solar and interstellar magnetic fields, demonstrating that even the most distant reaches of solar influence remain organized by electromagnetic forces originating in the Sun's corona. Long-term evolution scenarios based on IMAP's observations predict how heliospheric structure will change as our solar system continues its motion through different regions of the local interstellar medium over the next 10,000 to 100,000 years. These predictions suggest that significant changes in boundary configuration could occur on timescales much shorter than stellar evolution, potentially affecting cosmic ray environments throughout the solar system and influencing atmospheric chemistry on planets with substantial atmospheres. Such changes would occur gradually enough to be imperceptible during individual human lifetimes, but rapidly enough to create detectable signatures in high-resolution paleoclimatic records. Theoretical frameworks developed to explain IMAP's observations provide new insights into how stellar systems interact with their galactic environments throughout the universe, establishing our heliosphere as a prototype for understanding similar phenomena around other stars. The physics revealed by IMAP's measurements applies to stellar wind interactions throughout the galaxy, suggesting that the complex structures and processes discovered at our heliospheric boundary represent common features of how stars shape their local interstellar environments and how interstellar matter responds to stellar influence. The particle acceleration mechanisms operating at our heliospheric boundary may contribute to the galactic cosmic ray population through processes that operate around many different types of stellar systems, creating a distributed network of particle accelerators that maintains the cosmic ray background throughout the galaxy. These distributed sources complement the more dramatic particle acceleration that occurs in supernova explosions, providing a steady background contribution that helps explain the observed isotopic compositions and energy spectra of galactic cosmic rays. Magnetic field evolution at the boundary demonstrates that electromagnetic phenomena can create persistent, organized structures in the apparently chaotic environment where stellar and interstellar plasmas interact. These structures develop through processes that remain poorly understood, but appear to represent fundamental modes of magnetic field organization that emerge naturally when magnetized plasma flows encounter obstacles or boundaries. Understanding these modes becomes important for interpreting magnetic phenomena in a wide range of astrophysical contexts, from planetary magnetospheres to the interaction between galaxy clusters and the intergalactic medium. The emerging picture from IMAP's observations reveals our solar system as an active participant in galactic evolution rather than a passive observer of distant astrophysical processes. Our heliosphere continuously exchanges matter, energy, and momentum with the surrounding interstellar medium, contributing to the slow mixing and chemical evolution that gradually alters the composition of matter throughout our local galactic neighborhood. This participation connects the familiar processes operating within our solar system to the vast, slow currents of galactic evolution that have operated for billions of years and will continue for billions more. Only took us until the early 21st century to develop instruments sensitive enough to measure the subtle signatures of processes that connect our local planetary environment to the vast networks of matter and energy that flow between stars throughout our galaxy, revealing that the boundary between solar and interstellar space marks not an ending, but a transition zone where local stellar influence gradually yields to the ancient currents that have shaped the chemical evolution of matter since the first stars began to shine in the young universe. The data streams slow now, settling into the quiet rhythms of deep space observation as IMAP continues its patient vigil at the gravitational balance point between Earth and Sun. Years have passed since the spacecraft first began collecting the whispered messages from our solar system's edge, and the accumulated measurements have revealed architecture of invisible beauty spanning distances that dwarf human imagination. The energetic neutral atoms still arrive one by one at the detector arrays, each carrying its encoded information about collisions that occurred in the profound darkness beyond Pluto's orbit, where solar wind finally surrenders to the ancient matter drifting between stars. The heliosphere breathes still with the sun's 11-year rhythm, expanding and contracting like a vast organism that has pulsed through space for billions of years without pause. Solar maximum gives way to solar minimum in cycles that have continued since planets first condensed from the disk of gas and dust surrounding our young star. The boundary moves outward and inward by billions of kilometers with each cycle, yet maintains the fundamental structure that has shielded our planetary neighborhood from the harsher radiation environment of interstellar space throughout Earth's geological history. In the outer Helios heath, where temperatures cool from millions of degrees to mere thousands, solar wind particles that departed the Sun's corona decades ago continue their final transformation before joining the interstellar medium. Some become energetic neutral atoms through charge exchange with ancient hydrogen that has wandered the galaxy for millions of years. Others flow past the heliopause into true interstellar space, carrying with them the chemical signatures of our star and adding their infinitesimal contribution to the slow mixing that gradually changes the composition of matter throughout our local galactic neighborhood. The ribbon structure hangs across the sky like a cosmic question mark, still challenging theoretical understanding while providing hints about how magnetic fields organize matter and energy at the boundary between stellar and interstellar domains. The ribbon responds to solar cycle changes with the characteristic delays of phenomena operating across vast scales of space and time, brightening and dimming as pressure waves propagate through the outer heliosphere at speeds determined by local plasma conditions. Cosmic rays continue their patient probing of the heliosphere's magnetic defenses, testing every pathway through the turbulent structures that scatter charged particles across the boundary region. Some penetrate deeply into the inner solar system, carrying energies accumulated during million-year journeys across the galaxy. Others deflect back into interstellar space, adding to the population of high-energy particles that pervade the local interstellar cloud and trace the influence of supernova explosions that occurred long before Earth formed. The spacecraft itself drifts in its harbor at Lagrange Point 1, held in place by gravitational forces that have operated unchanged since celestial mechanics first achieved stable configurations around our star. Solar panels continue their quiet conversion of sunlight to electrical power, while radiators dissipate waste heat into the cosmic background radiation that still whispers through space at 2.7 degrees above absolute zero. Instruments cooled nearly to that same temperature maintain their sensitivity to individual atoms that remember where they have been. The local interstellar cloud continues its own journey through the galaxy, carrying our solar system through regions shaped by stellar winds and supernova explosions that occurred millions of years ago. Magnetic field lines thread through this medium with perfect straightness across light years of distance, guiding particle motions and organizing electromagnetic phenomena according to principles that operate throughout the universe. Temperature and density vary slowly across this vast region, creating weather patterns that unfold over timescales measured in millennia. Stars, much like our Sun, create their own heliospheres throughout the local cloud, each stellar wind carving its own cavity in the tenuous interstellar medium. These cavities overlap and interact in ways that create larger-scale structures spanning multiple stellar systems, demonstrating that the space between stars contains its own ecology of interacting phenomena. The physics revealed at our heliospheric boundary applies to these other stellar systems as well, creating a network of similar processes throughout our local galactic neighborhood. The measurements continue, each detected particle adding one more data point to humanity's growing understanding of how our solar system interacts with the galaxy that contains it. Radio waves carry the accumulated information back to Earth at the speed of light, bridging the 5-second gap between spacecraft and ground stations with streams of digital data that encode the architecture of boundaries spanning billions of kilometers. Time moves differently at these scales, where changes occur over decades and centuries rather than seasons or years. The heliosphere evolves with patient steadiness, responding to solar cycle variations and interstellar weather patterns according to laws of physics that have governed plasma behavior since the universe first cooled enough for electromagnetic forces to organize matter into the structures we observe today. The Sun continues its nuclear burning, converting 4 million tons of matter into energy every second while sending streams of charged particles racing outward toward the boundary where they will eventually encounter the processed remains of stars that died before our solar system formed. This process will continue for billions of years more, maintaining the heliospheric bubble that protects planetary environments from the full intensity of galactic radiation in the profound quiet of deep space. IMAP maintains its watch over these most distant reaches of solar influence, measuring phenomena that connect our familiar planetary neighborhood to the vast, slow processes that govern galactic evolution. The spacecraft drifts in mathematical stillness while the universe flows around it, carrying messages from the edge of everything we call home.